Okay. Hey everyone. Oh, he's hopping Discord. I'm excited to be a bit late today. Seth, hey, welcome in. Congrats on the first. So this is Saturday, so this is the second to last reading group we're having on this book here. It's been super fun. And yeah, so normally Finlux joins me. He should hopefully be here in a little bit. But anytime I was gonna get started anyway, it's a problem that what? Oh, it's the music. Oh my god. Okay, no worries, $10. Um, hey Rapture, how's it going? It's a problem that was sent to me by Dr. Cook. He had made it for one of the E&M classes that he teaches, and he said it'd be like we're probably in a good situation to try this problem out. So, actually, before I do this, I need to reread the little end of chapter summary that they have, because I haven't even thought about this since the last time we did the reading group. Hey Rex, how's it going? I meant to do this before the stream, and then I got distracted with Zach's stream. So I blame Zach. Definitely not my fault. Okay, yeah, these are Maxwell's equations. Pretty cool. I'll blame my lace on Zach too. There we go. Just shovel it all on Zach. Missed Zach's streams. Had a power cut from the morning till just now. Oh, that sucks. It was an interesting stream. He was doing like double and triple polar integrals, which are some of my favorites. I'm meaning to go back and relook at how he did one of those triple integrals, because he did it in a way that isn't how I usually do it. Yeah, Seth. So the way my streams used to be is that Tuesday and Thursdays are math days, and Saturdays are like reading group days, where I've been doing this reading group for the past like at least 6 months, probably more like 9 months or something. And then I do math afterwards. My schedule's kind of thrown out the window right now, but today, Saturday, and next Saturday are going to be the final reading group meetings, and I'll probably still stream on Saturdays at the same time, but it'll just be a normal math stream. And right now, Saturday's only a stream that I'm like committing to. Every other day, I just kind of stream when I feel like it and I have the time. I'm planning to, Seth, yeah. But just a warning, since you are like new here, if I don't have a question queued up, which happens pretty often, I study a different part of physics, mechanics, so I do problems out of this book. It's been my usual like downtime activity if there aren't if someone isn't asking for like homework help. All right, I don't think I need all this part down here. So let's read the actual problem from Dr. Cook. And it's usually about like 2 hours is how long I try to make this reading group session last. Oh yeah, sure. If they're already posted in Zach's Discord, you just like let me know where they are, and I can look at them as soon as this is over. Okay, sounds good. Two conducting disks of radius A form a parallel plate capacitor which is being charged by a constant current I. while the capacitor charges, and A by B rectangular loop of wire is fixed in place inside the capacitor as shown below. Top post is the first one. Let me look at it now in case someone posts something in the meantime. Is it the looking for formula one that Anders posted? Oh, okay, I see you typing that one. Okay, I haven't read the question yet, but I'll know to look at that one once I have time. Capacitor charge A by B rectangular loop of wire is fixed in place inside the capacitor as shown below. So I assume there's going to be some inductance happening on that rectangular loop of wire. If the field inside the capacitor is changing, use the ampere Maxwell law to calculate the magnetic field strength. B of R equals absolute value of B of R everywhere, or magnitude inside the capacitor. Radial distance R is less than A away from the axis of the capacitor. It's the ampere Maxwell law. So we want this bad boy right here. We probably would prefer the integral version though, right? There is an integral version, right? Because just getting the curl B isn't the exact thing that we want. Is there not an integral version of this? How do we actually get B then? We only know curl of B. Oh wait, if you know curl of B and you know that the divergence of B is 0, there is a way to figure out what B has to be. I forget how, but maybe I should just start on the first part. I should start by thinking about this part of the equation. Hey, Jordan.
Hi, Don.
Oh, hey, Finbox.
I made it.
Glad you could.
I was glad to hear you say you have not looked at this for a week because I haven't either.
Oh,
So
good.
it's a relief.
For some reason, my tablet is freaking out. Is it happy now? No? Dang, I reinstalled the driver for this thing, and that made it worse.
Wow.
Jordan, it's going good. Thanks for asking. How are you doing? Huh.
Yeah, I looked at this question yesterday and I thought, I don't think I know how to solve it.
I am not sure know how to either... What the heck? Okay, what if I just delete that? Wow, my tablet just isn't working at all. I might be stuck using my mouse. It's an interesting problem to have. Okay. Okay, sorry, this is... That doesn't work. Oh, no. Oh, wait, no, it does work. It's just an Excalibur. That's funny. Okay. I'm just gonna use my mouse for this, I guess.
No, I erased the thing.
Oh, no, Control Z.
Yeah, let me Control Z that. Control Z. Oh, now I wrote some letters on it I don't know how to get rid of.
Select. Oh. Wait. Maybe my tablet isn't the issue, because I can't use my mouse either. Okay, there. Now will my tablet work? Okay. Oh shoot. Okay. If I could just have like, I know how to delete that thing, but I just messed up the hotkeys for my tablet now. 7.
Oh, also, it looks like I'm an ornate salmon. I don't have anything against ornate salmon.
Yeah. I'd rather be an ornate salmon than a smoked salmon, so.
Yeah.
Oh my god. Why? Okay, my tablet still is acting super strange.
Is it Excalibur acting differently?
It's probably both, to be honest. Okay, now that button is working. Okay. And then...
You said I'm supposed to be out of Control Z, right?
Yeah, okay,
Oh, good grief.
that works.
Sorry.
No worries. I was gonna try and like drag a box around it and delete it, but that works too. Okay, well.
So, the Ampere-Maxwell law, is that the one that talks about the curl of the magnetic field?
Yeah. So, I need to make it thinner. Curl B. The first part is Faraday's law, mu naught J. Plus mu naught epsilon naught dE dt. And I don't like, even to figure out what the right hand side is, there's gonna be an extra step to go from curl of B to just B, and I think there's a way. I don't remember the way though.
Yeah, how do you uncurl a curl?
I remember the book saying that like if you force the divergence to be 0 as is true, then there is a unique solution. I don't remember how you get the solution though. But I figure if we can at least like figure out what the right hand, if we can at least get curl will be, I'd be happy with making some progress here. So the capacitor's being charged. So we are going to have a varying magnetic or electric field.
Yeah.
And J, can we? J I always struggle with to know what area we're talking about.
Yeah. We used this equation last week, right?
I think so.
Now, yeah, I want to say we did. I feel like this is the one we were using.
Yeah.
Maybe I should look at that. Because I feel like everything we did last week, we had to do. Yeah, how did we do it? How did we do that? We were integrating over surfaces last week. Can I on Discord, can I pull up the last week's
Yeah, I posted
notes
the
without like leaving this phone call here?
Yeah, if you go to like the reading group text channel, you'll still be in the call.
Okay, yeah, gotcha.
I just brought it up on stream too. Oh yeah, we took the divergence of each side there. For the first one we did.
That's what you just said, divergence. Maybe that's what we got to do.
Well, that gets rid of the B entirely.
What about the second question last week? And I'm looking at the solution you wrote for part B.
Oh yeah, we do have an integral version here, don't we?
That looks, is that?
I don't know where that came from. But yeah, that's one we want, I think.
I don't remember where it came from either.
Oh, they give it to us in the actual question, part B.
Okay, the integrated form of Maxwell's equation, the generalized form of Ampere's law. Is that the one we should use here?
That's what I think so, yeah.
Yeah, it feels like maybe that'll help us.
Yeah. Because that takes care of the J issue. If nothing else.
And so, right. So the C was a loop, and the S was a surface that was bounded by the loop.
Right.
Yeah, this week I'm really meant to try and review Stokes' theorem, but I didn't get that far.
Yeah, that one question that Critical asked is still bothering me. I really think I should be able to do it, but yeah.
Well, yeah, I know, and it was the same thing in Zach's channel today. He was doing some, the triple integral or the double integral in polar, and I got the answer wrong, and I thought, oh.
Yeah, I need to see
sometimes I wonder why they gave me this degree in math. It's like I should know this stuff better.
Feel the same.
Yeah. I want to say Calc 1 and 2 I feel pretty good with, but Calc 3, yeah. As soon as things go to 3 dimensions, I feel like I'm not doing well with it anymore.
Yeah, it's like fundamentally, I feel like it's not that much harder than the previous calculus classes, but actually executing the problems gets pretty challenging. Or like, you know, it is like just kind of like an extension of the stuff you learn in the previous 2 semesters, but just harder. Um,
Yeah, I know. Going from 2D to 3D, I mean, when you see the proofs of how they come up with the theorems, it seems pretty natural, but
just like it's way more like change of variables, I guess. Like a U sub is pretty easy to wrap your head around, but transformation from Cartesian to polar to cylindrical
yeah.
can get like
To
tricky.
to be fair, that spherical sector problem we were looking at, did you see that one Zach was looking at?
Yeah.
Like he kept calling it an ice cream. It looked like an ice cream cone.
Mm-hmm.
And I think to be fair, the way they wanted us to do that problem with a double integral was kind of, it felt unnatural, you know, because of of setting it up with like the way I ended up getting it was like vertical, like projecting columns vertically through that space,
Mm-hmm.
and so integrating the z first and then doing polar r theta on those z bound, what we got from the z bounds. But it didn't feel like a natural way to get that volume. So I don't know. I
Yeah,
guess
like
it's cool. It's cool that there's so many different ways to solve problems like that.
yeah, like I could see a natural way to do it with the triple integral, and then like there's a solid revolution way with a single integral. But like, yeah, that double integral way, I didn't know how to do it for myself. I was kind of getting like the Purcell vibes where you use geometry to avoid a triple integral, but I couldn't quite like
Yeah.
work it out. Um,
So getting back to Dr. Cook's question, where are we going to put our loop, where are we going to put our closed loop C, and where are we going to put our surface S? I wonder.
I assume the closed loop C is like the one that the book drew. You like enclose an entire plate in a bit of the wire, and then the surface of interest is going to be like that right edge.
Oh, this is just like the one in the book. You're right. It's like that doorknob shape they did in the book.
Exactly,
The
yeah.
doorknob handle. Okay. All right.
Um,
Cool.
so the line. Oh wait, but how does that work though? Because B. Oh yeah. Okay, so the B field, it is going to be in the same direction as this doorknob shape because it's going up or down. Um. So, and we only have to care about the part of the doorknob that's like on the right side because I think we can neglect any B field outside the capacitor. So
Yeah.
B times 2A, the length, is equal to mu naught I, mu naught epsilon naught. And now the electric field inside a capacitor, this should be simple, but it's either sigma over epsilon naught or sigma over 2 epsilon naught, and it's sigma's gonna be a function of time. Um,
We do need to get this answer as a function of the radius, or as a function of
ooh,
R. We want magnetic field strength B of R.
Right. So maybe my thing is bad, or yeah, maybe that's too much of an approximation to make for the electric field here. Unless the R less than A thing is, maybe it doesn't have to be a function of R if we do it, like that's just the approximation we're making. Like the result we get is only valid for R less than A. Because we usually approximate the field inside a capacitor as uniform, right?
Yeah, but that's the electric field.
Right, yeah. I If the electric field is constant, the magnetic field is constant?
We've got that current I, so we've got the electric field changing with time. Could we say, yeah, what is the electric field in the capacitor?
I think it is just sigma of t over epsilon naught. Because the field for an infinite plane is sigma over 2 epsilon naught, if I remember right.
Sounds right.
And we have two, approximately infinite planes. I feel like it's... I did confirm the field for an infinite plane. Is A, I guess, pi A squared? Yeah. Is it?
It might be pi r squared. Oh boy, now I'm confused because in the book, what they did was they made the doorknob wrap around the plate of the capacitor, and the curve was like around the wire part, right? This curve C was a circle around the wire part.
Right.
And the surface S was that weird, doorknob shape.
Mm-hmm.
So I don't know if that would be pi a squared, right? Because
I mean, it is the weird doorknob shape, but I think we only get non-zero flux through the flat big part inside the capacitor. That's going to be a circle. Also, this needs to be a derivative. The change of signal with time, which is probably dependent on I, and we can maybe work that out. Oh. Wait. Okay, I'm still not completely sure if this is right, but I feel like there's going to be some nice cleaning up. ddt sigma of t. We know that sigma is total charge per area pi a squared. But d by dt, pi a squared is constant, and d by dt of q is just I. So we're getting a lot of cancellations. for better or for worse.
Well, cancellations are good.
um, so it becomes mu naught I plus, I think just another mu naught I.
Hmm.
And so we end up with B equals I over A? Huh.
Is there still a mu naught in it?
You're right, there is.
So independent of radius.
Because I'm hoping that we're allowed to just say that it's uniform inside the capacitor. Or the electric field is uniform inside the capacitor, and hopefully that means the magnetic field is also uniform.
Hmm. So that's telling us that it doesn't matter how far away we are from the center.
Well,
Maybe we should check the units. Is this Tesla?
uh, it's a good question.
I'll bet it is.
And like always, I need to remember what the heck mu naught has as units.
Yeah, I know. That's why I got my physics book here. I'm trying to look it up.
Tesla meters per ampere. Oh, that's perfect.
Yeah, yeah, Tesla meters per amp, right?
Yeah,
Okay.
times amp over meters. So the units check out.
Okay, that's good. It's always reassuring. So,
I don't know. It feels right that it's something relatively clean, like the field inside the electric field inside a capacitor being kind of clean.
yeah, I want to know if it should be constant like that. Because in the problem,
Um,
he said, as a function of radius, but that might just be, Dr. Cook being
well,
Dr. Cook,
is
right?
it's true, but does Dr. Cook even say as a function? It just says 4 radial distances are less than a, and I interpret that as letting us use the sigma equals, or sorry, the E equals sigma over epsilon naught. Like that's where we use that piece of information. Oh, it is. Oh, sorry, B of R. I
Yeah,
see.
that's what I'm looking at. That's what I'm looking at.
Um, yeah.
So what about this? I mean, just like let's imagine we're right at the center of those plates, right? We're at a point right in the middle of those halfway between those plates in the center. That's telling us as this thing charges up, we've got this constant magnetic field there. Oh, yeah, it doesn't depend on time either, does it? For a constant current, it's not depending on time. Oh, well,
Well, no, the capacitor is charging, so
yeah.
the field is changing, electric field.
Yeah, electric field changing, but I'm thinking the magnetic field that we came up with. There's mu naught I over A.
Oh, yeah.
So if I is constant, then that thing's just a constant in Tesla, right?
Mm-hmm.
So yeah, and so if we went halfway out from the center towards the edge of one of those disks, it's the same value. I'm just trying to get an intuition as to if that feels like it's right. It definitely feels like it should be symmetric around a circle, right? Like it couldn't depend on anything but the radius. But should it even depend on the radius? Or how about this? Let's say we make the radius twice as much. We double A. We're going to get half as much magnetic field strength. Does that seem right? Maybe, because
Yeah, for
for
the
the
same amount
same
of
current, it's
charge.
going to charge the plate slower, right?
Yeah.
And if we double the current, we double the Tesla. All right. It seems like it could be an answer, doesn't it?
Yeah, it's simply an answer. Okay. I
Can you
mean,
tell me again, how did you get so let's see, you changed the dEdt to sigma t over epsilon naught. So that's just the derivative with respect to time of that electric field. No, it's not, because we're
um,
still differentiating it, aren't we?
right.
Okay.
At first I had dropped the d by dt and I added it back in later.
Yeah, I see that. So the electric field was sigma over epsilon naught. Yeah. I went back through the book trying to find that I couldn't find it in the book.
They
I
don't
didn't
seem
look
to
too
say it
hard.
specifically for a capacitor like this, but
Okay.
um,
But like you said, when you're inside a capacitor, you sort of, if you're neglecting the edge effects, it feels like you're near an infinite sheet, doesn't it?
yeah.
Okay. It's bringing back
Hmm.
vague memories from the first couple chapters. Yep.
Yeah. I, 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 I'm doing like the Gauss's law argument in my head though, and I feel like you can't enclose both sides, or if you draw your Gauss's law surface like through both plates, you don't have any flux. So where's that two coming from? Because I'm still only enclosing the charge of one of these plates at a time in order to get flux. Um, oh, it's because it's only going out one side.
Okay.
The flux, because for an infinite sheet, you have flux coming out of both ends, and then in a capacitor,
Yeah,
I think
yeah.
you only have it coming out the right side, or whatever side it's inside.
Yeah, that's right. Because if you're inside the capacitor, if you go outside, like the fields can cancel each other, don't they, outside? And in between outside they're interfering and inside they're reinforcing each other. So you get like double the strength or whatever.
Yeah.
Yeah, that's ringing a bell.
Okay.
Well, all right, let's say that's part A.
Yeah, I think I'm comfortable with it. Um, part B, I've been reading it as we've been working on part A, and I'm confused because it seems like the loop is like parallel to the wires. Like the bottom part of the loop is along the axis, which means there should be zero flux through it, right? Or maybe not.
I want to say that's an optical illusion. I'm thinking of the loop being sort of parallel to the plates.
Okay, that would make more sense. Well, wait. Okay, wait. That would make sense for the electric field
Yeah,
because the electric field's going
that's right.
across like that. Maybe it is right for. Oh yes. Okay, because I remember they showed a picture somewhere that the magnetic field in a capacitor like this goes in circles, so it actually should be parallel to the wire to get flux. I think that's how.
Oh, so you're,
Yeah.
so you're saying it's not an optical illusion. It really is just in the plane of the paper, that loop.
Yes.
And it's at right angles to those plates. Oh, all right.
Okay. That makes more sense.
Oh, because right hand rule, right? You sort of point your thumb along the direction of current and your fingers are curling where the magnetic field's coming. The magnetic
Right.
force lines or whatever they call them, magnetic field lines. Okay.
Yeah. And if it doesn't depend on radius, then this flux becomes really simple, not an integral. Which I guess we're back to our previous question, but
Yeah.
well, okay, if it did depend on radius, we would have to integrate from 0 to A, we'd have a B out front of mu naught I or R dr, I think. But we'd end up with ln of 0 here and get something that's diverging. Maybe... Ooh. No, we should get 0 from that piece, right?
Are you saying if we just sort of replace the A with R?
Yeah, like if I assume if this thing did depend on radius, we would get the exact same result, but with an R instead of an A. That I assume that. Maybe I shouldn't have, but I think both of the A's in the setup in part A would become R's.
Oh, you're saying, oh, I see. You're saying this A here would turn to an R, and then the A we get to sort of do through all the business over here. Yeah, what? Wait a second now. These A's wouldn't cancel. Yeah, I don't know. What I do like about this, which kind of feels cool, when you did all that work and you got the second term changed into being the same as the first term,
Mm-hmm.
it kind of feels like calculus problems where you're trying to maximize the area given some constraints or something, and you end up getting, you take the derivative and set it to 0 or whatever, and you get two terms and they turn out to be equal, or you get, you got the given amount of fencing for a rectangular region, and it turns out you want the rectangle to just be a square, like the two
Oh
dimensions turn
yeah.
out to be the same. So that's what I thought was cool when these two things both turned out to be mu naught I. I was like, oh yeah, that could be, that feels good in a way.
Hey, Bubbles.
What was I?
Um, now I'm debating if it should diverge. It probably shouldn't, but what's happening in the flux right on the axis? Is it 0 or infinite?
Well, don't you want to just stick with our previous answer and just change that R into an A?
Yeah, yeah. Let's debate there at least. um, capital phi. Was he saying sub b? Yeah. Is equal to just the magnetic field times area. So mu naught IB. Oh, wrong B. It's nearly Bill.
Makes sense. It would depend on B, right? Because if you make that rectangle wider, you've got more flux coming through it. So that makes good sense.
Okay. And A drops out because if you increase, because we're kind of making the loop equally as tall as the capacitor, so if you increase them both at the same time, they're going to kind of scale at the same rate and cancel each other still.
Yeah. Yeah. Right.
Okay. I think Cook said that we could add on a part C.
Oh, he did?
For R, do the same things for A, but for R greater than A.
Oh.
And for that part, I'm a little lost there
Yeah.
because we never really talk about what happens outside the area we care about. I feel like. Oh, good luck with your finals,
Feels kind of
Freddie.
like that
Sorry, go on.
that question from way back in the first few chapters where we were finding the electric field at a given radius from like a uniformly charged sphere.
Um,
I've always got this graph sticking in my head, and it kind of went up linearly from until you hit the radius of the sphere,
oh, right.
and then it fell away like 1/r² or whatever.
Yeah,
So I'm wondering if we'll get something similar here, except we didn't get anything increasing in part one. We got something constant.
right. Um, yeah, I thought to calculate like the field outside of the middle area of the capacitor, you need to do some crazy integration. It's usually not. I wonder if there's some simple answer that you can just like say it's 0 or something just by thinking about it. But I think to actually work something out like mathematically is probably really difficult. My instinct would be to say 0 though. Or at least any field out there is going to be pretty negligible.
Actually, how about this? If we go far enough away from it, then the magnetic field doesn't understand there's a capacitor there. The magnetic field just kind of sees it as if it's just one long uniform wire with current I flowing through it. Does that feel right, or does that
Oh,
not?
yeah. That seems like a good idea. Um, yeah, I don't know if we could just take that as an answer, or if that's something that we would like check the end behavior for and expect it to look like a normal wire.
Yeah, okay, yeah, I agree. What is that formula again? Was it U naught I over R?
Um,
The magnetic field around a infinite wire?
that sounds like it. That will be it. Mu naught I over 2 pi r.
Oh, 2 pi r, yeah.
So Ampere's law. Um, I think that's the best answer I could give. Like, I don't feel equipped to like think about the situation outside of a capacitor, otherwise at least.
Yeah, right, because they call them like fringe effects, don't they, near a capacitor?
Yeah.
And you see a lot of problems where they say like ignore fringe effects.
And I like living in that land.
Yeah.
I don't know. I'll read this out. Um, but I think that's good enough for me at least.
I guess we show it to Dr. Cook later and sort of see how he grades us, and
Oh, speak of the devil. Hey, Cook.
oh, there he is.
So I think we just came to a conclusion for the first problem that you sent us, including little like part C that you added on. Um, Oh,
oh, you're in an ad. Yeah, what we came up with is we came up with a constant magnetic field between those capacitor plates. Oh, he won't be able to hear me if he's in an ad. Oh, sorry.
yeah. No worries. It like whenever I'm typing someone's chat, it's always like the exact moment when I say hi is when an ad plays. I try to like time it when I just see an ad or something. Oh, okay, here he is. All right, the field.
Oh, he says it's not constant. Oh, all right.
Okay, so here's most all the work that we did. Um, we use the integrated version of the law. I wonder if we could simply, if we do just switch out the A's for R's. I don't quite get why if the electric field is uniform though. Um,
We were trying
yeah,
to use that.
we basically drew this for our loop.
Oh, it was a rectangle. I was thinking of that doorknob shape still.
I think it's all the same because we only care about the right edge.
Yeah, because the doorknob shape is arbitrary, isn't it? Isn't that what Stokes' theorem tells us? It's like the thing that
Hey Ben, the correct loop should be
Stokes.
what? Not the doorknob or the rectangle.
Maybe we got to find a nice loop here that's going to help us. How about a cylindrical loop that sort of encloses one of these capacitor plates?
What's a cylindrical loop? Oh
Well,
shoot, I'm undoing something.
it looks kind of like a capacitor plate, but it's been extended, or a pillbox, right? He calls it a pill. We were talking about that pillbox and that Morin and Purcell called it. Maybe some kind of pillbox surface that could cut through the center of one of the plates and extend out on both sides.
Huh. I'm wondering about drawing a circle around one of the plates of the capacitor.
Go again through Ampere's law used to derive magnetic field around a wire. Oh, yes, that would be useful.
Okay. Well, we have a wire with current I flowing through it. We would draw an Amperian, Amperian loop, I guess, parallel to the axis. And we know it's parallel to the magnetic field here. Yeah, Cook, you should still have access, so just hop in. And so the line integral around this thing evaluates to b times 2 pi r, the circumference of the circle. And r is the distance away from the axis.
Okay.
I think it's for an infinitely thin wire, but I think a thick wire is the same, more or less. It's equal to mu naught I. Because I is just equal to j in this scenario.
Oh, good grief. Here's mu naught over 2 pi r.
Yeah.
If I had these concepts in my brain, I wouldn't have to ask you, oh, what's the magnetic field R away from a, it's so easy.
This one's kind of stuck in my head for some reason from chapter 6.
Nice.
And so that's why I was imagining maybe we want to do the same thing as here, but in a circle around one of the plates. Because I think that still counts as a current if the plate is charging. Although I'm not quite clear on that.
Well, if you had a circle, I don't know if you want to go outside the capacitor, right? You want to sort of stay inside it and intersect it, maybe. Oh, wait, would that work? No, we can't intersect it, can we? Because then there's current flowing in it.
But like, they intersected it in the doorknob shape.
Hello?
Hey,
Hey,
Hey, what's up?
nothing much.
Long
having
time no.
fun with physics.
Is there a way I can view the Excalibur? Because I think
Yeah,
the stream is a little lagged behind.
I'll just send you the link because I put it in a weird place in the Discord. Um,
Okay. Oh, and our dirty DMs. Okay, good.
yeah.
Okay, dope. Okay, yeah. So maybe I watched a little bit of your last stream on displacement current, and I feel like maybe you guys are struggling a little bit conceptually with the topic, which is
Mhm.
something I definitely
Maybe,
encountered.
maybe he says.
Well, I'm trying to.
We definitely were.
I mean, when I'm teach this topic, I noticed I don't think a lot of my students really got it, even though I tried my best. So I would say there's like one thing that's important. There's two sentences that I think if you just remember these two sentences, they'll help you a lot with displacement current. Um, but maybe a preface to that is you got to distinguish between regular current, which is often called conduction current because it's the conduction of electrons like in a wire. So we
Mhm.
have conduction current and displacement current. Okay. And the two sentences are one is how they're the same and how they're different. And maybe to preface this or like ask you guys, could you answer this question? Like how are conduction current and displacement current the same in one sentence and how are the two different in one sentence?
I want to say conduction current is actual flow of electrons, whereas displacement current isn't.
What is okay, that's good. That's correct. But what is displacement
And
current then? Before
displacement current is somehow some kind of a field, some kind of a magnet change in electric field to sort of counteract the. I
I
don't
think
know. I guess like
I would just stop there. That is correct. So it's just a changing electric field in space. That's what a displacement current is. So, so yeah, as you said, conduction current is the transport of electrically charged particles, like electrons typically, and displacement current is just a changing electric field in time. And so that it might feel wrong to say that because the word current, you don't think, oh, there's a changing electric field, but that's what a displacement current is. That's why I think Morin says maybe the terminology is bad. Although I disagree with him on that statement because of the other part, the second half of this. So that sense is how the two are different. One conduction currents, the conduction of charged particles, displacement currents of changing electric field. That's how they're different. How would you answer if they're the same?
They're both caused by the movement of electrons.
No, they're not.
Well, I
Displacement
guess
current
it's
is not. It's
is like
just
changes in the
yeah.
movement, but
No, no. If displacement current has nothing to do with moving particles. You got to get that out of your head. Maybe
aren't they
Moore is right. The
caused
name is
by?
bad.
Okay, yeah,
No, no, or not necessarily. No.
okay.
For example, like if a light that's hitting your eyes right now, that's an electromagnetic wave that has a changing electric field. So that has an associated displacement current with no moving particles. You really have to like just you know disabuse your mind of this notion that displacement current means moving charged particles. It doesn't. And this capacitor is another great example. There's a displacement current in between the two because there's this electric field that's building up as it charges, but there's no particles moving between the two. So how
hmm,
are the two the same though? That's still on the table.
energy, carrying energy.
I mean, that's true for both of them, but I think there's a more precise answer here. And you kind of have it written down right now, actually.
Oh no. Um,
They're both well, something to do with Maxwell's equation here.
Yeah.
they're both related to the magnetic field.
Yeah, even more specifically, they both create a magnetic field. So to
Oh,
summarize, I would say they're the
oh,
same. They both produce a magnetic field. That's why this changing electric field, which seems nothing like a moving charged particle, like you typically think of current. So why call it a current? Well, because it produces a magnetic field in exactly the same way as a current.
Huh.
That's why the name is the way it is. And so, in fact, this equation here with curl B equals, if you factor out the mu naught,
Mhm.
um, you'll get mu naught times J plus epsilon naught dE dt. So this equation is telling you epsilon naught dE dt is producing a current in the mathematical exact same way as J. So
Hmm.
those two things, displacement and conduction current, are the same and exactly the same in how they produce magnetic fields. But they differ in that one is moving charged particles and one is a changing electric field in time.
Hmm.
Huh. Hey, Reaper. Okay.
I didn't mean to do that. Okay. So that kind of gives you a hint of this problem. We're trying to calculate the magnetic field produced inside the capacitor where there is no conduction current. What's producing the magnetic field inside?
The changing electric field.
Yeah, exactly.
Time changing.
Or equivalently the displacement.
Displacement current. Okay.
Right. Two ways to say the exact same thing. So, and in fact, I'll tell you that this is kind of anticipating the answer, but one way you can think about this that's equivalent for the magnetic field is that you can imagine just remove this capacitor altogether, and instead imagine this infinitely thin wire goes into a fat wire, the same radius A, and then goes back to a thin wire.
Hmm.
Those two setups will be the exact same in terms of the magnetic field produced. Why? Because this Maxwell Ampere law, the Ampere law with the Maxwell correction, tells you that mathematically the conduction current and the changing electric field, the displacement current, produce magnetic field in exactly the same way. So in terms of how magnetic fields are produced in this problem, the function of the capacitor is just to widen out the current.
Oh. Wow.
Because there's a conservation of current, including displacement current. So what happens is this conduction current is all bunched up in this infinitely thin wire, goes in this capacitor, which charges up and creates a changing electric field. You can think of that as that conduction current spreading out over that radius A into a displacement current, only in terms of how it produces a magnetic field, not in terms of any particles moving. There's no particles moving. And then on the other side, you can think of that displacement current bunching up again into a conduction current. So actually, if you remember, I don't know if you did this problem when you did Ampere's law, but there's like this problem of a uniform current carrying wire of thickness A and calculate the magnetic field inside. Did you do that problem?
I think it was an example.
Maybe.
Do you remember what the
Um,
result was?
for the magnetic field for a thick wire is mu naught I small r over 2 pi big R squared.
Right. So the magnetic field isn't constant, but it increases how?
Linearly.
Radially.
And
Yeah.
that's what you're going to find here, because exactly I'm going to say it like again and again. The displacement current that is affected in between these plates produces the current magnetic field in the exact same way as this conduction current. So you're going to get a linear. The magnetic field increases linearly away from the center. That's
Oh,
what you should find.
just like the electric field inside a uniformly charged sphere as you come
I
away
was
from
just
the
about to
center.
say that. Yeah, exactly the same thing.
Yeah,
Yeah.
Okay.
because
So now,
we were talking about that a second ago because we were looking at your part C where you got to go R is greater than A, and I was thinking
Mhm.
about that
Well, so
same.
what's the
Oh,
scaling going to be then? You should be able to
I
see
want
it.
to say it falls away as 1/r or 1/r squared. Is it 1/r squared maybe?
Um, it's going to be 1/r because it's
One
just
over
like the
R.
wire that Don did. It's going to look just like a wire outside.
that is the answer that
Oh
we
man,
said. Okay, so it was actually your same idea there. Like you said that, Fembox.
yeah, that graph. I was thinking of it. I don't know why
Right.
this problem it reminded me of it.
But I think just for practice, so it's good to go through this. So the math is going to be the exact same as that uniform current in a thick wire, but it's good to go through it in this problem just to kind of familiarize yourself with the idea that a displacement current really does produce a magnetic field in exactly the same way. So with that, maybe you can see the Ampere and Maxwell loop.
I think it's just a circle parallel to the axis, like the same as the magnetic field that this thing is like producing.
Right. At a arbitrary radius r.
Right.
Right. And then the magnetic field is swirling, so B dot ds along that will be constant. That's because you have the symmetry of the problem. So that was the
Yeah.
problem with the loops you were suggesting earlier. B.ds over those loops is going to be really gross, and the integral doesn't turn into a product.
Yeah, we're stuck on that because they draw a similar shape in one of the examples.
Yeah. So
Um,
that's to motivate the idea that. So maybe in live this discussion, I think that derivation might make a lot more sense to you. But what they're trying to say there is that imagine you had Ampere's law without this Maxwell correction. In other words, the only thing that can produce magnetic field is conduction current. Imagine that's what you thought. And you look at this capacitor. It would look like the current, in terms of not moving particles, but in terms of magnetic field production, disappears in the center. It would look like there's a magnetic field around the wire, and then you shift over and there's no magnetic field anywhere inside the plates. And then you go again to the right more, and then you get a magnetic field again. So the purpose of that picture with the doorknob thing is they're trying to say, you should expect there to be a magnetic field inside too by Stokes's law, Stokes's theorem, I'm sorry, mathematically. And physically, with the way that happens is that the assumption that only conduction current produces magnetic fields is just wrong. And Maxwell showed, or mathematically using this argument, that another way, equivalent way to produce magnetic fields in addition to the conduction current is this displacement current. So yeah, maybe now just talking with you guys, maybe the name is bad. Maybe I do agree with Warren, but it's a current in terms of how it produces the magnetic field. It's not a current in terms of anything moving, any particles moving. And maybe just to clear up terminology too, Ampere's law is a statement that curl B equals mu naught J. And so here I use Ampere-Maxwell law to distinguish. Ampere-Maxwell, I mean the full thing with the ddt. So another way to say this is that Ampere's law is strictly speaking wrong in classical E&M because it doesn't have this correction. Although sometimes people call the full Ampere-Maxwell law just Ampere's law again. You'll see that sometimes. I think that's really confusing. So I like the term Ampere-Maxwell.
All right. Yeah, before you got here, we were kind of discussing, I don't know, for 5 or 10 minutes, whether or not we felt like our answer should be independent of the radius. And, I don't know, we kind of convinced ourselves that it was okay. But I think we both felt a little bit hesitant.
yeah.
The radius R or A?
The radius R, yeah. Because we got an answer that was it didn't have an R in it, right? It was just B equals mu naught I over A, I think is what, 2 mu naught I over A.
Just mu naught I over A.
That's correct units.
Yeah, we did check.
We checked the units. We did check them.
That's good. I mean, that's so it's not an egregiously wrong answer.
I'll take it. Not egregiously wrong. It's a good enough standard for me.
Well, you jest, but like when you teach physics, you'll get all sorts of things like mu naught I, and it's just like, come on, dude, doesn't even make sense.
Okay, so I got excited and I started correcting the work already. Is it mu naught
okay, this looks
IR with 2 pi a squared?
So dimensionally, this is correct, right? Because it's mu naught I over a length, and we know from the wire formula that's what it has to. So the units look right. I worked this out the other day. Let's see if I can find it.
It does kind of match the form of the thick wire.
Yeah, that's what I got.
Actually, exactly, it matches. Yeah. Okay.
Yeah. So I like to take that and write equals, factor out everything times R just to make the scaling clear.
Yeah.
That's the preference I like.
There you go.
Yeah.
And so I like this problem too, because this is on a final exam, because in part B, it's like just a straight up flux calculation, but requires
You've got to do an integral now.
easy integral.
Yeah.
Yeah.
So that's the other part. That's the reason why I thought this was okay I thought it was okay to be constant because if we had it to be over R, we would get a diverging like ln of 0 situations. Like, maybe we're okay, but no.
Yeah, it's linear.
Okay, I mean that's not a very hard fix though, because we just have B times the integral from 0 to A of the magnetic field.
Right,
squared.
yeah.
RDR.
Yeah, I like to write like one more step where I write DA is BDR, but like this is what you'll get. So this is perfectly correct.
Okay. U naught B 2 pi A squared. 1/2 R squared 0 to A. Oh, we're losing the A's again. Okay. U naught B 4 pi 8 pi.
Yeah, Don, before, remember you said it makes sense, even though we had the wrong answer, you said it makes sense that it doesn't depend on the radius A of the capacitor
4 pi.
for part B, I mean.
Yeah.
So,
What was your argument for that?
well, because your rectangular loop is sort of growing at the same rate as the
Oh, it's getting the whole
capacitor.
thing.
Yeah.
Yeah. Yeah, good point. Yeah, that's the answer I have too. This is 4 pi. Okay, and maybe it might be worthwhile just to go through C, like just but telling yourself it's displacement current instead of conduction current. I mean, you'll get this result. I don't know. Maybe you don't want to do it.
Which kind of said it looks like a wire from far enough away.
Well, but it's a bit stronger than that. It looks like a wire of conduction current, even though there's no conduction current.
Okay.
Yeah, but yeah, that's otherwise perfectly correct. Okay, so yeah, I thought this problem would maybe clear things up for you guys a bit.
Yeah, thank you.
Yeah, that's a good one.
So okay, I think this might be a good time if you're up for it to do the other problem I sent you, because that problem delves a bit more into this conservation of current that I claimed earlier in this discussion, but we didn't really kind of argue to you that there's a numerical equivalency between the amount of conduction current I that comes in, and maybe it has to be a part D for this. You could calculate. Yeah, how about this? Maybe a part D where you calculate the total displacement current inside the capacitor, and you should get I, proving that there's a conservation, that all the conduction current turn into an equal amount of displacement current. So one way you can think about this is, so look at your part A where you've written here.
Oh.
Can I write here?
I think I half did this when I was figuring out what sigma of T is.
Oh yeah. Okay. So in this A we write curl. How do I write on this?
I switched to the pen tool on 7.
Okay. Sorry, I'm being a boomer. I get error every time I mark.
Oh. I don't know why that would happen.
Let me rephrase. So if you factor out the mu naught on that equation, that's what I was trying to do. I'm refreshing. Let's see. Okay. Oh, I'm a thick boy.
There's like thickness controls on the left side, but this is readable.
I like being thick.
All right, fair enough.
So I'm going to call this JC just to make it ultra clear. That's this conduction current, but it's what we just call J for the rest of this book. And recall that has units of current per area. So this term here that I'm taking excruciating amount of time to write, that's often defined to be the displacement current density, J sub D, because it adds in the same way. So if you just call this thing current, then you can kind of like pretend Ampere's law doesn't really change. It's mu naught times the current density gives you curl B. So that's the origin of the name. But in modern way, maybe you say, yeah, it's really, there's maybe it's better just to call it DDT. But anyway, so the way to approach this part D I'm suggesting is calculate this guy. That's the displacement current density, and then integrate it over the circular face of radius A. And that'll give you the total displacement current I. And I think it is going to be similar to what you're doing there with sigma. And then
Yeah.
that'll show that the total current is conserved.
What was your subscript of C again?
Conduction, just to make it
Induction. Yeah.
clear.
Okay. Yep. Gotcha.
But the key point here, to zoom out a bit, why this is important. What does Faraday's law say in words heuristically?
I need to look at the actual equation again, but the change in magnetic flux does something. I can't remember the other side
Right,
of
so
the
that's the
equation.
integrated form. But the
Right.
microscopic form says that a changing magnetic field in time produces an electric field. And
Right.
so if you imagine trying to start an electric E&M wave before Maxwell had this correction, you would have maybe imagine you have a changing magnetic field. That's great. It produces a changing electric field. But that changing electric field does nothing. And this, like, what you try to create this EB wave just dies out. What Maxwell realized is with this correction, that changing a magnetic field, maybe called B, can induce a changing electric field. And then now, because of this Maxwell correction, this displacement current term, there's no charges moving, no particles, but this changing electric field will then in turn give a changing magnetic field. So you have this like reinforcing oscillation in empty space between EB. And that's what light is. Like the light you're looking at your computer screen at. And this is like one of the most like the greatest moments of theoretical physics because, and you'll do this if you go to the end of this chapter, when Maxwell took these equations with this Maxwell correction and calculated the speed of this wave, he got 3 times 10 to the 8 meters per second. And that was known at the time to experimentally be the speed of light. So he realized, oh my God, this is what light is.
Yeah. Imagine working that out.
Oh yeah, dude. Yeah, I mean, I think Einstein talks about it. Like that's got to be one of the greatest moments ever any human's ever experienced. Yeah, so well, the picture I'm drawing here with these loops change, that's kind of heuristic. That picture you have, Don, is more accurate.
Yeah, I assume it's not necessarily true for every single wave that's possible, but I'm just thinking about how the maximum of E occurs at the minimum of CB and vice versa.
Yeah, so that takes a bit more math. So I think it'd be good to make sure you understand the displacement current and then the wave thing.
Okay.
I'm just trying to maybe get ahead of it a bit, but this is where it's going. This is the importance of this. Because in empty space, like in outer space, there is no conduction current. And yet light can exist. So somehow this magnetic field has to be created. And it's by this other mechanism, not the conduction current, or the displacement current, i.e. the changing electric field.
Oh yeah, that's what they said later. They said, look at Maxwell's equations, but let there be no matter, right? Which means no charge density and no charges anywhere. And so some of the things can't turn into zero, but you still get the E and the B that are able to exist. Yeah, okay.
Yeah, that's the vacuum equation.
The vacuum, yeah. That's right.
So that's how the story goes. Like magnetic field around a wire feeding into a capacitor doesn't make sense unless somehow the changing electric field inside the capacitor produces a magnetic field. And then you go to empty space where that's the only way you can produce a magnetic field. And that this reinforcing effect is what explains how light can exist in empty space.
Yeah, when he wanted to introduce the displacement current, his first section in this chapter was called Something is Missing.
Exactly. Yeah. So there's like it's a story in your head. Like a lot of physics is a story. You gotta know how the story goes. But if you're convinced, are you convinced that the total current is conserved? I think it might be worthwhile just to calculate this JD and then integrate it over the disk?
Yeah, so I think the surface we'd be drawing is the same as kind of like that loop, but we'd take R to be equal to A. So JD is equal to D. I can see what the math involved is going to be like, but I'm trying to justify it in like physics. I know that we're going to integrate from 0 to A
Yeah,
of something, or of the
you have to
thing
use
that
a
I did with sigma. Sorry, what?
So I guess we need E as a function of R then, don't we? This time.
it's uniform. It's a capacitor.
Oh, yeah. Sorry.
So you just use you kind of have the right symbols floating around here already. Yeah, excellent, excellent.
And so I think I probably need an integral maybe somewhere earlier in the work too, but
No, you're good now.
okay.
Everything's good so far.
Q over. Well, I guess maybe here we need an integral for area. No, I'm
No.
confusing myself now. Sigma
the
is
place
just
uniformly.
Q
Yeah.
2 pi.
Nope. It's what's
Not,
sigma? It's the
charge
density
per
per
area.
But not
This?
that radius. This is the sigma on the disk.
Oh, okay. So I or
the plate. Sorry, maybe that's a better way to say it. Excellent. Yeah, and now that pi squared is not changing. That comes out, and dq dt is just I.
For some reason, what do I think we need an integral? Oh, because I was stuck on the magnetic field being variant, but that's not necessarily, or that's not the same for the field. Okay.
Excellent.
Oh, it's the same thing you did on the line above there.
Yeah. I was just I want you to kind of see it in a coherent way. But yeah, exactly. So, and now if you multiply both by the area, which in general would be an integral, but in this case isn't because it's uniform, you get the conduction current that's coming in turns into an equal amount of displacement current inside. And then so I might put IC on that, just to be clear. That's what the importance of this equation is, that there's a D on the left and a SC on the right. So if you integrate or multiply, in this case, ID is IC. That's the important thing I'm trying to just emphasize.
Yeah. So you're saying the conduction electron current turns into changing electric field current.
In the same amount, yes.
Yeah, with conservation, yeah.
Yeah. So I don't think the textbooks usually don't emphasize this enough. They say it, but I really like to drill this down. It's an equal amount, So it's kind of like was it Kirchhoff's law, where you have like currents, all conduction currents flowing into points have to be conserved. But this continues to be true even when you throw displacement current into the mix. So maybe that's another motivation to call it current. It's like a current, and it produces a magnetic field in exactly the same way, and it's like a current in that it's conserved like this. But it's not like a conduction current in that it doesn't have anything to do with moving particles.
It kind of makes sense, because if it wasn't conserved, then when you went from the left capacitor plate to the changing electric field between the plates, and then from that changing electric field between the plates to the right plate, then we'd get a different current flowing in the right-hand wire than we did in the left-hand wire, wouldn't we? It kind of feels like I can say ID on the left wire equals IC between the plates equals ID on the right wire.
Flip D and C, but yeah.
Maybe I got the D and C backwards, yeah.
But yeah, that's a perfectly valid way of thinking about it. Another way to think about too is like, if the displacement and current inside were either greater than or less than the conduction current flowing in, the magnetic field strength, like at a large R, but maybe left of the capacitor versus over the middle of the capacitor, that would change, right? Like if you say you had less, say the displacement current were numerically less than the conduction current flowing in, then the magnetic field here would be stronger than the magnetic field here, because it would be like a less amount of current producing the magnetic field.
Hmm.
But that's not reasonable because of just the mathematical theorem of Stokes' theorem. Like you could draw your surface like this or this.
Oh,
So that's the doorknob argument he was giving. Is like, even if you use pure Ampere's law with this surface, you still get, like you expect that these magnetic fields here to be the same whether you're above the capacitor or at equal radius, not above the capacitor, just above the wire. That's another maybe intuition to have why these currents should be equal, because they have to produce the same amount of magnetic field outside. And maybe a good exercise to do would, maybe just staying on this a bit, just to maybe finish it up. Could you take this PDF image of the disk and blow it up and maybe try to draw the E and B field everywhere inside? That might be worthwhile.
Let me get a copy of this to make it easier.
the E field and the B field.
Yeah, because they're coexisting in there.
Uh,
And maybe at a fixed time.
I just pasted in a second image down below here and blowing it up.
You guys got my inner teacher coming out again. It feels good.
I love it. Maybe even bigger. Okay. Well, I think the E field is just kind of the thing that we already know from way earlier, just a uniform. I don't know if
Which way
field
was
lines or vectored arrows are better, but
Right, good.
all the same length, all like perpendicular.
And here's another thing to point out too, maybe not draw, but just I'll point it out. As time increases, these arrows get bigger, right? The electric field points more and more to the right.
Okay. Yep.
Right.
So,
Yep.
so DE dt will also point to the right. So as a vector,
Okay.
JD, the displacement current density, if you drew that, would also point to the right. So this
Okay.
conservation of current is also true directionally. The conduction current flows to the right, the displacement current flows to the right, because E is increasing to the right. And this can get non-trivial, like it will in the next problem, where like an electric field can be decaying, so the derivative will, yeah. Anyway, so that's the electric field. So what does the magnetic field look like?
It's pointing towards us through that rectangle. Well, towards us in the upper half and away from us in the lower half.
Right.
Well,
Like
it's yeah, circular. Yeah.
and also getting stronger, right? As you get, so
Oh
way I
yeah,
like to draw it,
radially. Right.
I like to draw it like this.
Yeah,
the
if you have
dots
a better way, I'll get rid of mine.
How do I?
Oh, with the
What is it?
dots and the X's. I've seen it that
Yeah,
way.
but I have my own
Oh,
I haven't seen anyone do this, but where I make the dots bigger.
Okay.
How do I?
Make the dots
okay.
bigger for stronger and smaller for
Yeah,
weaker.
exactly.
Okay.
So I would do like something like this, and then this is the axis. Oh,
Okay.
oops. And then
X is for yeah.
this is a shit drawing because I'm on my mouse.
I think I get the idea. Is it really weaker the closer it is? Oh yeah, because it scales linearly.
Yeah, that's what you
Okay.
showed here.
Yeah, that's weird.
It's 0 at the center, so there's no magnetic field at the center.
And
That's true of a finite wire too. If you have a radius A finite wire carrying a uniform current density J, at the exact center, there's no magnetic field. In fact, that has to be true by symmetry, because if it pointed in some direction, you could rotate the wire and it would point. Or you could say it points along the axis, but that would be with the current. That would be unusual.
Hey, math major.
Yeah,
Okay.
symmetry is good. Symmetry's so helpful.
Agreed. Okay, so do you guys feel good about this? Do you want to attempt the other problem I sent? It's a little harder.
I feel much better about
Sure.
this now.
Yeah, same.
I looked at that. I didn't really look too closely at that second problem. It was like, oh, maybe the first one is a good place to start anyway.
Okay, I'll hop off here, but I'll be watching the chat.
Okay. So you're setting us free again.
Well, I feel
No,
like
he's
I don't want to like rob you of the learning opportunity. Let's put it that way.
Okay.
But I'll be in the
all right.
chat.
Thank you for
he's
the help.
just throwing us in the lion's den. That's all.
Yeah.
Well, I think you guys got it now. So this problem I don't think will be too difficult.
Okay.
All right.
Thank you. Hey, Omer. All right. I put it in just below the big image.
Okay. Yeah. Got it.
Yeah, 6 parts. I don't think I'd even read it yet. So, too large conducting plates
No,
of
I
area A.
didn't read it.
Okay. Located at x equals plus or minus d over 2. The left plate carries initial charge plus q greater than 0, and the right plate is minus q now less than 0. Time t equals 0. The volume between the plates is filled completely with a rectangular slab of material x. Oh, we haven't done dielectrics. But I think it's just like you have a slightly different epsilon naught.
Yeah, something like that.
Texture constant kappa, infinite resistivity rho less than infinity. The capacitor then begins slowly discharging via conduction through material X. What is the capacitance C between the plates and the resistance R between the plates? Yeah, I just haven't done dielectrics at all before. What? That's probably chapter 10 this one.
I've done them, but I forget. But you're right about it. It means you just sort of, because you're replacing air with something else, you're changing the value of epsilon naught, or epsilon naught, I think.
Yeah, see they do it in chapter 10. Let me just look at, maybe the chapter summary will be enough to save us here. You guys can set kappa equals 1, just ignore that part of the problem if you want. It's not a central displacement current concept. Maybe I shouldn't have added it. Oh, okay.
So we just multiply the value of the capacitance without the dielectric times the dielectric constant. Is that what we do? I think the dielectric constants are dimensionless, if I'm not wrong.
I think it's something like that, but I think like saying we probably just ignore it because, or I think letting kappa equals 1, like he's saying, just basically means that there's no dielectric. Replace epsilon 0 with, okay.
Kappa over epsilon.
Seth, dielectric would increase the capacitance of this thing, but we haven't covered it at least in this reading group yet, so we're trying to work out if we just want to deal with it or ignore it. Hey, 750. Also, just worry about the resistivity rather than the capacitance.
All right.
Okay.
I think it's just some kind of scaling factor.
Yeah.
I mean, it works out to be, I think it works out to be a scaling factor. Obviously, conceptually, there's more going on.
And now how do you calculate capacitance again?
Yeah, I know.
Over
How do you
V.
call it?
think. I mean, we are just like given it in the book too that the capacitance of a parallel plate capacitor is epsilon naught A over S. Oh, nice. 750. But I mean, do we probably have to worry about the resistivity? Would that change the V? I mean, we could just write V. It's the same Gauss's law derivation. Really? Oh, I guess if kappa equals 1. I mean, if... This is weird to me, because what's the difference between a capacitor with some resistive material inside and just a normal circuit with a resistor? It feels like the same thing to me. Because everything is in contact with each other. There's
Maybe in
this
this problem it is the same thing, but in general, in general, there's no leaking through the dielectric. Like there's no actual electrons moving through it.
This is a leaky capacitor.
Yeah. Yeah, we did a resistivity problem before. Remember, we had to integrate over the volume, I want to say. How did that work again? Yeah, to calculate, didn't we? Isn't that how you calculate resistance? You integrate do a volume integral over resistivity.
I think so, yeah. And here's just a rectangle, so the result is probably simple. Cook just says that the resistivity is finite. I hope that also means that it's constant. Oh, unless... I hope, yeah. Like, maybe the resistance, it is constant? Okay, so... it's a rectangle. Rectangular slab. Okay, but we don't necessarily know the dimensions of this thing. There are no tricks in part A, just trying to scaffold the problem.
The only trick involved in part A is remembering all the formulas from the last 8 chapters of this textbook, which to me is kind of a big trick.
I think it's just like R equals rho A over L then.
Yeah, R equals rho L over A.
Oh, okay.
Now I'm only saying that because I'm looking at it on a page out of my textbook here.
Okay, I was about to look it up. This is from the final homework semester review was the goal. Okay. C is equal to A epsilon naught over D. Okay. All right, Omer, sounds good. Sleep well. There's no L. Right, yeah, we do need to...
Yeah, we got to get the right letters.
Us
Right?
getting the wrong answer would be an L, but other than that, there's no else.
The L would just be D, wouldn't it? In this case, yeah, lowercase d.
Yeah. Okay. So I guess that's part A. Suppose the capacitor has charge Q of t at a generic time t greater than 0. Use Ohm's law to find the conduction current I sub c t between the plates in terms of Q of t. Well, if I is equal to V over R, and V is equal to Q over C, I think we have all the pieces of the puzzle, as long as I'm careful with what Q is. I guess it's 2Q naught? Because each plate has Q naught?
I think
Or is
they.
it only one side?
I don't. I think you only use one of them, don't you?
That sounds more correct.
I think the Q in the formula is the charge on one plate.
Okay. And then C, we...
So that's dq dt.
This is a lot of fractions.
All right, but everything's constant more or less there, right? Except for the Q and the I.
Yeah.
Okay, we're in business. I should say you're in business. I'm just watching.
Oh, yeah, it should be, it's not Q naught, it's Q of T.
Q of T, well, yeah.
This is too many fractions for me to do the mental math, so...
It is a lot of fractions. I'll applaud you for having many fractions in one term there.
Yeah. Q of T, A. No, the A's cancel. Cancel, 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 cancel. Okay, so epsilon naught rho. Okay. I of T is Q of T over epsilon naught rho.
And the I of T is dq dt, isn't it? So we got a differential equation here.
Okay.
Yeah.
Is that going to be... Oh, yeah, that's part C right there. So conduction current discharges the capacitor remain right.
Oh, I was jumping the gun. I thought we had to do that in part B, but we don't, do we? In terms of Q of T.
Yeah.
Right.
Separation of variables. Oh, okay. We're not allowed to use an integrating factor. Try to scaffold this a lot. If you get a chance, you should. Whenever Zach like recaps his dissertation, he kind of like talked a lot about like how much like you can scaffold problems. It was kind of cool. Row. Okay. And then separation of variables. 1 over Q dq dt minus 1 over epsilon naught rho.
Does this mean rho times epsilon naught has units of time?
Oh. There's something like that. I think like the book definitely makes a point about some combination like that having units of time somewhere, some way. I forget what the units involved are, but epsilon naught definitely, like, you multiply with something and you get like inverse time or something, I think. The method I taught my students was separation of variables. Oh, okay, fair enough. It is a lot easier than integrating factor anyway. Not QT. Oh, looks like Cook is making Wolfram Alpha do the units there for you, $10. An ohm meter times epsilon naught is seconds. And that near looks like the speed of light, but it's the wrong magnitude. Or, I don't know, 8, I don't know, something. Resistivity is ohm meter. Oh, right.
Oh, it is seconds. Oh, thanks, Cook.
C is probably a bad constant to use. Dang it.
I remember one time I asked my physics teacher in the hallway at my school. I walked up to him and I said, "Hey, Dr. Al," I said, "do you know what a farad times an ohm is?"
Oh yeah? What was it?
You guys know what a farad times an ohm is?
I don't.
I might have it wrong. I think I have it right.
Is a farad magnetic flux? So Tesla meter squared?
A farad is capacitance. Like they measure capacitance in
Oh.
farads, like picofarads or
Wait, so yeah, if it is capacitance, then it should be coulombs per volts. Cook is saying time, RC constant.
yeah, that's where I got it from. That's where I thought of the problem. Because from doing circuits, I learned that, tau is this time constant and it's R times C.
Nice.
Anyway, he got it. Yeah, he knew it.
No one for inductive circuits. Right, yeah, the book talked about LC circuits a bit.
Yeah.
For
Yeah,
LR?
it's RC for
I don't remember, but
I think it's L over C or C over L. It's one of those.
R over L is inverse
What am I
time.
saying? Yeah. What am I saying? Yeah, it's not
Or it's just time.
R
No,
over
inverse
L.
time. No, yeah, Headbox was talking about there's a similar thing for LC. Right, LC? Yeah, no, LR. Ugh.
Yeah, it was my bad. I was screwing up.
No, I think I'm the one who said the wrong thing, but there's an R over L for a time thing too. Okay, for part C, I think beginning to make sense. Q naught e to the minus t over epsilon naught rho.
Yeah, RC and then L over R. Yeah.
Whenever LC is the period of oscillation in an LC circuit. Okay. Oh, I should look into that now, differential equations of circuits, but I guess it makes sense that an LC circuit would oscillate and not drop off like an LR circuit. Okay.
Yeah, in chapter 8, they went through a bunch of this stuff.
Oh, you goofed? Okay. Yeah, I want to go back and read chapter 8 and then also 10 and 11. I want to read the entire book. Square root LC is the period of oscillation. Okay. Easy solution for Q of T from part C to calculate the conduction current density J sub C of T, magnitude and direction between the plates. I think that's basically...
All right. Sorry, I took my eye off the ball here. So don't
No
we need
worries.
a plus C in here?
Uh,
Let's see.
no,
Or
we
did
get
you just
a...
kind of do it as you went?
I should have done a plus C in that step, but I remembered to add it in that step there.
Oh,
And
I
put,
didn't see it there.
like
There it
C
is.
sub
Yep.
0 because I didn't want to confuse the capacitance.
Now, can't we work out? Oh, you did work out what it was. The C0 turned out to be Q0. That's
Yeah.
right? Okay. Okay, and we've got exponential decay of the charge on the plate. That seems like it makes sense, right?
Yeah, because it's just discharging. Okay. Current density.
I'm still surprised that rho times epsilon naught turned out to be in units of time. I mean, come on. There's just too many units in physics, aren't there?
And they have those weird combinations
aren't
that
there
are
too
so
many
clean.
units in physics? Sometimes I feel like I could have been good at physics. It's just the units that held me back. There's just too many of them.
I almost wish we
There's
didn't
just
like.
way too many of them.
It probably would get too complicated, but like the Henrys and the Farads, I kind of want to get rid of them and just use the base units all the time. It'd be so much easier for me to remember, I feel like. Maybe it wouldn't be, but
Yeah, maybe it wouldn't be. I don't know.
Newtons too. I don't know.
I think once you get familiar enough with all the individual, branches of physics, you're like, okay, I'm glad I have a unit to work with here to make the problems a little bit more concise. But boy, when you're first learning it, there's just so many different kinds of units.
Yeah.
So now we got to use the solution from part C to calculate conduction current density, magnitude and direction between the plates. All right, so here we go.
So it's just
We got Q as a function of time.
yeah, I think for J we're drawing a rectangle that is like a two-dimensional rectangle that's contained in our rectangular slab. It's basically the rectangular slab, just take a 2D slice. Which famous physicists are seconds and meters named after? True, Puig. You never heard of John Seconds and Steve Meters? Current density.
I think the only reason they're not named after physicists is because some things were discovered before physics was really had a chance to get off the ground,
I mean, meters were defined. Ooh, I don't know. I think things were standardized officially like in the 1900s, weren't they? Like it was like a UN thing, the actual SI system, but maybe they used meters before that. I don't know. Look at the first line of B. I mean C. Something wrong with it? Or is it helpful for part D? You have the current already since you have Q of T, just divide by the area. Oh, I wrote the wrong thing. It should be I of T, yeah. Oops. Not charge per area, current per area.
Oh, that makes more sense.
So it's minus Q over epsilon naught rho over A. We weren't given an axis, right? So we can just say from the left plate to the right plate. Oh no, we're given X. So we could say X hat, because I think it's going in the positive X direction. Neglect the minus sign. Oh, there shouldn't be a minus sign. Yeah. Or it's like the vector would take care of that. Well, it's a function of time, right? Yeah. Epsilon naught rho A Q of T X hat. And that should be current per area. Minus Q over epsilon naught P.
So should we
Oh,
bring
A
in
goes
our
on top.
QT?
No, it doesn't. Sorry, what from Lux?
I was thinking we could bring in QT from part C. Oh, no, I'm jumping the gun again. Maybe that's the next question.
That's what I was about to do before. I think we should, based on the phrasing of the question. Yeah.
Yeah, you're right. We should.
Because Q naught can go on top.
Yep.
E to the minus T over epsilon naught rho X hat. And Seth, you definitely could have a minus sign out front, but you want a minus sign on the vector too, and then things get weird. Okay. Oh yeah, Freddy, that's life.
The left plate was positive and the right plate was negative. So that, I think that makes sense.
Oh, to simplify, yeah. So, yeah. Oh. Okay, yeah, fair enough, Cook. Okay, I think that's the answer for part D. Conduction current points from the positive plate to the negative plate, yeah.
Yeah.
Use your solution for Q of T from C. So part E. To calculate the electric field E of T, magnitude and direction, and then the displacement current density J sub D between the plates. Okay. Well, I think E of T is equal to sigma of T over area that's constant and still in the X hat direction. This is pointing from positive to negative. And sigma of t. No, I'm sorry. It's sigma of t over epsilon naught. That's just the field inside a capacitor. And then sigma is charge per area, and we know an equation for charge. So Q naught, I guess I'll do over epsilon naught A e to the minus t over epsilon naught rho. Oh no.
Hey, we got a responsible pelican here.
You are cool. Oh. I was expecting like you are driving me crazy or something, but I'll take it. Bye. Oh wait, that was the second Cook, because I see that. So I think Cook was the echidna, so maybe Cook jumped in again, or someone else got the link. That is a Cook thing to do, though. I don't know. Wasn't you? Oh.
I wonder
We have a
who it
mystery
was.
in our hands.
Yep.
Oh, I wonder, can someone just look at the link at the top and type that in? That might be it. If they're willing to type in that entire thing. All right, well, at least people are being cool about it, if that is possible. Oh, wait, that was you, Freddie? Over in the YouTube chat? All right. I guess for videos are working with chemistry. I know the organic chemistry tutor on YouTube has a good channel, also for math stuff. Funny enough. Have the AI transcribe it into a copy of the link. Oh, yeah. All right, so that's good to know about Excalibur. It's not private. Well, I've been going through all these pains to, like, you know, not put the link out there. It's just at the top. Okay, it's good to know. All right, well, thank you for not, like, drawing something bad.
That's funny. That's funny.
I applaud your dedication to typing out that entire thing.
Yeah, I got to keep that in mind next time I'm watching somebody stream on Excalibur.
Yeah. Start adding on to their work. Yeah, I could just crop it out of the view. But I won't do that now, and I'm too lazy. I'm probably going to be too lazy to do it in general. Did I think this is an answer for the electric field.
Let's see. Yeah, I think so. Okay, so now the displacement current density is basically epsilon naught times d e dt. So let's check that.
Okay. Tyler brought me here to your channel. I'm just a high school kid. Fair enough. Oh god. All right. Fair enough. If you don't mind getting out of the Excalibur, though, at this point, thank you. It's a Stokes theorem or flux and induction calc. Stokes theorem is probably like lurking in the background somewhere. We haven't used it explicitly though. There's a lot of like flux involved in this, and Yeah, like we're basically just got the flux. That's what the current density is, this J thing. So not okay, yeah. And I guess we already know what. Oh no. Okay, yeah. We still have to take the derivative of this thing. Are we getting epsilon not cubed?
No,
Oh no,
one
never
of
mind,
them
just squared.
cancels.
Oh, I see. Okay, good.
So Q naught. Epsilon naught rho A. Is that how we've been writing it? Yeah.
Um, that looks good to me. Cook is asking, can you explain in words why JD points to the left?
Can you explain in words why JD points to the left? Let's see, because, so what's happening here? The capacitor is discharging. So the electric field's getting weaker. So dEdt is pointing left. Yes, the EDT is pointing left. So the displacement current would point left. I think that's right. Does that make sense, Don?
Yeah, I mean, I just think of it like it has to produce the same exact field as the wire around it, magnetic field. And so it kind of has to be going the same direction to achieve that. But it's also just like the formula just kind of gives you they point in the same direction. Oh, apparently there's ionized beasts on YouTube. Type the link. I think I have multiple people claiming credit, but fair enough. He's pointing to the right and decrease magnitude, so D. Oh, true. Okay. Oh wait, why is it? It's pointing. Oh, I didn't even realize it was pointing to the left. Oh my god.
Yeah, that's that negative sign.
Yeah. Okay, I guess that makes sense because yeah, it's pointing the same direction as DEDT, and DEDT is pointing to the left because it's decreasing. Okay.
So if we look at JC and JD, aren't they just equal and opposite? Yeah, they are.
Oh. That.
Oh, that's part F. That's part F. Part F says
Okay.
show that that total current flowing between the capacitors is always zero.
Reverse me. No, it's all good. Ionized beast.
Oh, yeah, because in this case, we don't have a wire connected to these plates, do we? I mean, we don't have it's just some capacitor isolated in space, and
Oh,
it's discharging from the left plate to the right plate.
yeah, like electrons aren't crossing from one plate to the other. So there can't be current.
Well, they're crossing from one plate to the other, but if you think of the system as just just put a big circle around the capacitor, there's no wires coming out of it, right?
Wait, I thought the two plates just kind of influence each other with the fields. There's nothing literally transferring between them, right? Or I've been talking about capacitors this entire time. Cook, I see Cook just jumped in, maybe because I said that.
No, I just thought this might be a good point to discuss because yeah, Finvox is. I think you want to say what you said again.
Yeah, I'm just thinking of the capacitor as just being isolated somewhere. in space and there's no wires connected to it. It's just sort of two plates. And so there's
Right.
no current flowing outside. Like in the last problem, we had a constant current coming towards the left plate and the same constant current away from the right plate. But in
Conduction
this
current.
problem, conduction current, thank you, yeah. But in this problem, we don't have that, right?
Yeah. So the material X is inserted. If you go up to the problem statement, yeah. So I think that's a good way to think about it. But before
Oh,
X is
yeah.
inserted, you have this capacitance charge in empty space, and there's no current of either kind flowing. Then you just pop in this material X inside, and that creates a conduction current. But we saw the statement of conservation of total current from before. Whatever conduction current is created by this discharging through material X is compensated by the weakening electric field, which gives a displacement current pointing the other way. So there's zero total current before and zero total current after.
Ah,
Okay. Yeah, when I said the thing I said before, I forgot there was the material that we inserted in between the capacitor plates.
Yeah, I think like
Um,
that's the downside of so many scaffold. Like when I give my students, I think by the time they get to F, they're like, I just make it in, so they don't like. I'm trying to like break it into steps, but F is the main point. Like, so these two problems would kind of go together. Like as Fivloff was saying, if you're charging a capacitor, you create this changing electric field, or in other words, a displacement current to kind of carry the total current through. Only in terms of how magnetic fields are created, not in terms of moving particles, of course. And this is the inverse situation where you have a discharging of this, you create a conduction current to discharge, and that's compensated by an equal and opposite conduction current to keep the total current zero like it was before. So these two problems should be thought of in pairs.
hmm.
So here's
Now,
another way to think about it. Yeah, go ahead. Sorry.
I was going to say, what if instead of the way you set the problem up, so you had the charged capacitor, the isolated capacitor, and then the way you discharged it was to put the dielectric in between that wasn't, infinitely resistive, so it was kind of making it leaky. But what if instead of doing that, you just had the capacitor that was charged connected to a circuit, and then you'd thrown a switch to allow the current to flow away in the other direction?
That would be
Um,
just like the last
that would
problem.
be just like the one we did before, wouldn't it? Except all the arrows are going the other way.
Right.
Okay, yeah, gotcha. Oh,
Is
and
that, yeah,
then,
you could
but then
just
also
you could
the current wouldn't be constant because it would be
prove. Yeah, and that's
okay.
true. So and yeah, that you could add that as like a third kind of problem to pair with this, like a trio. Yeah, so then the electric field would be decaying inside, but not due through a conduction through the capacitor, but through the outside through the rest of the circuit, like you said. Like the charge would go down, the electric field would go down, and that would induce um, a displacement current, which would be equal and opposite to the. I'm sorry, would be equal, strictly equal, even in direction two, with the conduction current going through the circuit.
Right. Yeah, I see it.
Yeah, so I made in the last problem I made the external current constant just to simplify it. It was a exam problem, but this was a homework problem. I'm realizing they actually pair pretty well together. And in fact, I think
Yeah,
this would be
this
a
is
good.
a good problem.
This might be a good way to motivate. So there's this argument in the text about this doorknob surface motivating why displacement current should produce a magnetic field. This might be another way to also give that same motivation. What's the magnetic field everywhere in this geometry in this problem?
the magnetic field everywhere.
Yeah, in this problem.
Um,
Wouldn't it be the same as in the last one?
Oh no.
No,
Think about
we
part
found
F.
E.
part F says a constant current of 0. Total current flowing between the capacitor is 0.
What does ampere Maxwell law say? curl B equals.
0. Ah, curl B equals 0.
In this case, yeah. In general, it says it's mu naught JC plus JD. So the two things can produce a magnetic field, JC and JD. But here they're canceling. So what's the magnetic field here?
Oh, 0.
0. Just like it was before. Before I put an X, it's just a static charge capacitor sitting there. There was no magnetic field. And I don't create one by putting this material X in between either. But imagine you hadn't read this chapter yet. Like, imagine, let's kind of reverse the argument here. Imagine you hadn't read this chapter. Just mentally put yourself in that space. You could say, a student could come to you and say, well, Professor Don, I put material X in there. This is capacitor discharges, so I have a current running through between the two plates. Ampere's law says that current should produce a magnetic field, but you're telling me there's no magnetic field? Why not? How would you answer such a student? The student would say,
Well, yeah.
everything I've learned now says that currents produce magnetic fields. And when you discharge a capacitor through its interior like this, you're producing a current. And yet you're also saying there's no magnetic field. How can that be?
Well, that's when you'd have to explain this whole displacement current concept.
Right. Exactly. That argument fails to take into account the second way you produce magnetic fields, which is displacement current. So it's not like, maybe one way to teach this, like an ahistorical way that's maybe intellectually more economical, would be just say, don't even teach Ampere's law, just teach Ampere-Maxwell law straight out. Yeah, forget you even just learn Ampere's law. There's what can produce a magnetic field? Conduction current, displacement current. Those are the two things. The only reason people get confused is because you learn from Ampere's law that conduction current produces a magnetic field, and you don't learn about this for another month or two. And it's like someone's like, oh wait, there's actually a second way, and they can cancel together or add up. But you should kind of,
so maybe you could tell the student, well, you're not wrong that the conduction current is producing a magnetic field, but what you haven't learned yet is that there's an equal and opposite magnetic field being produced in a different way, or that you haven't learned about yet. That's canceling.
Exactly. Yeah, that's a good way to say that. Sure. That changing electric field inside will give you a canceling magnetic field.
Well, good problem.
Well, I learned this from Halliday, and well, actually, I don't know. I probably didn't really learn this properly until I had to teach it, to be honest.
Yeah.
Because
Yeah.
textbooks don't really explain this very clearly. But I thought, if you understand these two problems and those two sentences I said earlier, the conduction current and the displacement current are alike in how they produce magnetic fields. And that's not even strong enough. They produce magnetic fields exactly the same way, and they differ in that one is moving charges and other is changing electric field. If you understand those two sentences and these two problems, I think you got the idea.
Is there a way that we can just figure out that the conduction and displacement currents are canceling without doing all this math? I'm sorry if you said that and I missed it. Like,
Yeah,
do we know
I would
intuitively
just
why?
say I would just say before you inserted this material, when you had the charged plates, what was the magnetic field?
0? Or
0.
yeah.
Right. There is no magnetic field. And just moving this material in place there doesn't change anything in terms of the magnetic field. That's like the high level intuition, I think.
Okay. Okay. Fair enough.
Another way to say it is the total current's conserved. Maybe that's a clear way to say it. Before I put the material X in, there was no current of either kind. There was no conduction current and no displacement current. When I insert the material, I'm not inserting any new current. So whatever conduction currents is created has to be counterbalanced by equal and opposite displacement current to keep the total current what it was before, 0. And because current is what produces magnetic field, keeping in mind there's two types of current, conduction and displacement, 0 current before and 0 current after means there's no magnetic field because there's nothing to produce it.
Yeah, I guess that makes sense. We haven't actually added any like charge. Okay.
Yeah. And maybe to make another statement just to make this even more evocative is like if you just took a charged metal sphere in your hand, and maybe your hand was like rubber glove or something, so it could just discharge. You just had some charge in your hand. You start shaking your hand around. You're going to produce a magnetic field because you
Okay,
have
yeah. You're moving charge
because you have a
around.
changing electric field. Oh well,
Or
yeah, you could
well,
think of it that way too.
yeah.
uh, well, yeah, I see what you're saying. Yeah, well, that's kind of the intuition you have to break, though. Like magnetic fields are not strictly produced by moving charges. They can also be changing electric fields. So maybe that was a bad example. Um, yeah. So yeah, maybe the capacitor is the best example, the one they use in the book. But,
Yeah, it's all good. I do feel way more clear on what the hell displacement current even is. It's still kind of
Seth,
weird, but like I feel like I understand it more now.
yeah, I'm glad. I thought these problems might help. Um, Seth asks if the same thing applies to Earth magnetic field. The Earth magnetic field is produced just by a straightforward conduction current. It's the moving charges in the Earth's core. It's very hot, so the charges in the metals they have enough kinetic energy to free themselves from the metal. This is called ionization. And so when the Earth spins, it spins this hot charged liquid in the middle of the Earth, and that moving charge creates a magnetic field. So, but that's just the standard conduction current, and you would get the the magnetic field produced by that current just from the old Ampere's law without the Maxwell correction. So this is actually like a pretty small effect because, and the reason this wasn't noticed in experiment. So Ampere's law was a noticed in experiment. If you just you put a battery to a wire, produce an electric field. Sorry, you put a battery to a wire that produces a current running through that wire, and you hold a compass, you'll see the compass deflect for pretty, um, pedestrian currents and batteries and stuff. But this wasn't observed experimentally at the time because even if you have a quickly changing electric field, that mu naught, that extra factor of epsilon in front makes the displacement current very small, like in just terms of numbers. So if you had a discharging capacitor and you put the little compass needle inside that discharging capacitor, uh, typically this would be pretty small. That's how the textbooks explain it, or at least you would might if you see a magnetic field, you might say, well, it's the wire nearby that's leading into the capacitor. Um, yeah, so this is kind of a how to say it, like a little tricky pedantic point that you need to complete Maxwell's equations. And the real important thing is because this, like I said before, this is what allows for electromagnetic waves to propagate.
Yeah,
Changing,
yeah.
yeah,
That what you were just saying, that reminds me of something I thought of before. So if you think of an electromagnetic wave, so it's orthogonal, like you can think of it as like sine waves, right? That are like a E wave and a B wave that are sort of moving together with each other.
right.
Now, don't they care? Do they? Does it make any sense to say like how much energy is being carried by the electric wave, or do you need the electric and the magnetic waves at the same time? You can't have one without the other, right? You need both of them.
Uh, yeah, I'd say electric wave that doesn't exist.
Yeah.
You need the changing electric field produces a changing magnetic field, which produces a changing electric field. So they have to go together.
And there are
Um,
ways to calculate the energy carried by each component. Is that true?
um,
The reason I'm asking is because I'm
yeah,
wondering because I feel like I've read somewhere that that the E field is strong and the B field is weak or something. Is that true? Like, yeah, Don's got
It's
it on
because E
screen. We
equals
got E
BC, I
and we
think.
got C times B, right? They
right,
got the extra C there, which is 3 times
right.
10 to the 8. So does that mean
But
the B?
they carry equal amount of energy though. I think because there's this magnetic field densities like
Yeah.
the amount of energy in each goes like the amount of energy in an electric field goes like E squared, and the amount of energy in the magnetic field. Actually,
Like E squared.
I'm trying to remember. It's 1/2 epsilon naught E squared for the
Okay.
electric field energy density. That's energy per unit volume. So if you just have an electric field in space, there's energy in that field just existing. And that, even for like a static electric field in between a charge capacitor, that's not doing anything. And there's the same statement for a magnetic field. If you have a wire that's carrying a steady, unchanging current, that'll create a static magnetic field circling around it. And that has the energy density, energy per unit volume that goes, I think it's 1/2 mu naught times B squared. And then you can show that, yes, E equals CB for the strengths of the field for E&M wave. So numerically, E will be larger, much, much larger. But
So does
if
it,
you
does it,
if you
is
calculate
that,
the energy density, they split the total energy of the wave was split half and half in the two fields.
yeah, yeah. But maybe that's because the wave with B has the factor of C in it, right? I don't know.
So E equals CB makes E is much larger than B in terms of numbers, but also
Yeah,
the energy
3 times
density
10
for
units.
B is 1/2 mu naught B squared. So you got mu naught in the denominator. So that means for a small b, you can still get a reasonable energy density,
Because mu naught
which is
is 10 to the minus 12, isn't it?
something like that. Yeah.
So if you divide by it, you've got 10 to the 12 times as much.
And
All right.
conversely, the electric field energy density is 1/2 epsilon naught E squared, where epsilon naught's upstairs. That's
Yeah.
smaller by that multiplication too.
All right.
So it turns out that they have, if you calculate the energy density in E&M wave, exactly half of it is in each part, but neither could exist independently.
Well, good. I want it to be half and half. Yeah.
Yeah.
All right. All right.
Right. So the way this is introduced, like the displacement current can seem kind of like silly and pedantic. Why introduce this? Like, okay, now that I had one way of producing magnetic field, now I have two, displacement or conduction, versus whereas before I only knew about conduction. But then, the key next step is that in empty space, there's no conduction current. So if I look at this E&M wave, how can it exist? Well, I understand how the changing magnetic field can produce a changing electric field. That's Faraday's law. But without the displacement current, I don't understand how that can reverberate back to the changing electric field, create the magnetic field. Because if you only know Ampere's law, and the only way you think magnetic fields can exist is by a current, you look at this E&M wave in empty space, you say, where's the Amperian current that's producing that magnetic field? There's no moving charges to be seen. Well, it's the displacement current. That's the changing electric field, which doesn't have anything to do with moving charges. It's just called a current because it produces a magnetic field in the same way as a current.
Well, very good.
Can I ask a stupid question?
Sure.
So Faraday's law is the voltage, or script E equals minus d capital phi dt. Like changing magnetic flux produces a voltage.
Well, I would call it an EMF, not a voltage.
EMF. Okay.
Has
But-
units of voltage, but yeah.
If that can work in a vacuum too, I thought you need like some kind of closed loop to have an EMF. Like, how does that work in a vacuum? Or there is no loop?
In EMF, it just means E.ds integrated over a closed loop is non-zero.
Okay, so you don't need a physical wire.
No.
Okay.
And this actually goes back to like your mechanics knowledge. So like maybe answer this question. Oh yeah, no, actually this had to do with that question I showed you for my first midterm too. Do you remember that circling electric field?
Yeah.
In fact, do you still have it in your in that DM? That's very relevant. Yeah, so I made that problem in anticipation of this point right now in this semester.
I should have it somewhere in my downloads. It's probably going to take too long. Let me just scroll through the DMs.
Oh, you have the solution there.
Your bonus problems. Oh yeah, I see you posted your solution there. I'll bring it up on stream.
So this is a good question, which I didn't understand. Like the first time I took E&M is, why do we sometimes say voltage and why do we sometimes say EMF? They both have units of volts, right? But it's because the magnetic field. Sorry, well, these two statements are going to be true. I'm trying to think what's the best order to say them. In Faraday's law, let's just say Faraday's law, which you've known before you got to this chapter. For Faraday's law, the electric field that's produced by that changing magnetic field is non-conservative. E dot ds is path dependent.
Mhm.
You can't define a potential. So it's not proper to say there exists a potential. The amount of work required to move against that electric field that's produced by this changing magnetic field is path dependent because it circles like this.
Yeah, I
Right.
remember this question. This is the one I got wrong.
So that's why, like, well, if you, yeah, I mean, it's confusing. It's a confusing point, which is I'm trying to poke your intuition. But like, yeah, if you don't understand this point, it's very natural to say, why do we say EMF and do a script E all of a sudden when we're reading this book? Why not just call it all V? They all have units of volts. But it's because when you say the word potential, you're implying there's a path independence of the work, like in the gravitational potential. If I go like from height 2 meters to 3 meters, it doesn't matter if I do a squiggly path or I go straight up, it's the same amount of work in either case because
Yeah.
that's a conservative field. The electric field produced through Faraday's law by a changing magnetic field is non-conservative because it circles like this way. So you can't say potential. So I say EMF, and what that's supposed to like alert you to the fact that the amount of work you do depends on the path. So if I do two different paths from a point A to a B, even if those A and B points are the same, the EMF could differ.
Right. Okay.
You don't know the EMF between 2 points A and B if I just tell you A and B. You have to be given A, B, and the path. Okay, and the same thing is true with the magnetic field created by this displacement current. So if you remember that first problem we did today, that changing electric field in the charging capacitor created a circling magnetic field. The top it pointed towards us, the bottom pointed away.
Mhm.
Yeah.
So if you integrate
Yeah, here it
B.ds,
is. This is that field. Yeah, I see it now. This is that field you drew.
right, so that's a circling field too. So that's not going to be conservative. So there's no magnetic potential here. That's a non-conservative field for the same reason. Um, so uh, the magnetic field produced by a changing electric field and the electric field produced by changing magnetic field, neither of those produced fields are conservative.
Huh. Okay.
Um, so your question about EMF alerted me that. What did you ask again? You said why
Uh,
is EMF?
it's like if there's no physical wire to produce an EMF around, how does the equation in a vacuum work? And I
So
think you answered that, or I don't know, maybe there's more.
yeah, so the EMF is just a statement of how much work you have to do against the field moving from a point A to a B and a given loop. So another way to say, another way to frame your question that might make the answer more obvious is to say, like, if I talk about the gravitational amount of work to move a mass from 2 meters to 3 meters high, why do I not actually have to do it? Or like, why don't I have to move it along as like a wire or like what are those toys in the dentist's office they got with the beads on the beads with
Yeah,
a
yeah,
hole in them?
yeah.
But you could say, why don't I actually have to do that to know what the potential between these 2 points in the field is? It's an abstract statement about fields, even if you don't have particles moving in the fields.
Okay.
Like like the gravitational potential energy between one height and another height is a well-defined number, even if you don't actually move something between those 2 points. And the same is true for EMF and electric field. In fact, it's not even a physics thing, it's a math thing. If I have a vector field in 3-dimensional space,
It's
I
a
can say
conservative vector field.
or even say you have a non-conservative field. Let's call it what do you want to call it? Like F? That might imply force in your mind, but it can be anything. Let's imagine you just have every point in space I have a 3D vector. So it's like f vector is a function of x, y, z. Now, if I give you a point A, B, and a path between those points, I can calculate this. I can define this value, which is f dot ds along that path. That's a number, and you would say that's the quote unquote like EMF or mathematical EMF between those 2 points, given and given that path for that vector field. And then if that vector field that f turns out to be conservative, then you'll realize that it actually doesn't. All those paths will be the same. You have the same quote unquote EMF. So
Okay.
you
Yeah.
don't need a wire to talk about EMF because it's a mathematical thing for a vector field.
Okay. And so I think it's more like how we initially. It's now it's non-conservative in the situation, but we're back to how we defined electric potential initially with a positive test charge going through a path. But this time it depends on the path rather than being just point A to B.
Right. And in either case, do you need a wire or any charges actually moving between those two to talk about it?
We don't. Yeah.
You just mathematically calculate E dot ds along the path.
Okay.
The same way you don't need to move any charged particles around to determine an electric field between 2 points, right? Or at a point. You don't have to actually put a point charge there to work it out. You can just sort of.
Sure. Yeah, I mean, that's a good way to think about it.
Yeah, like
Okay.
you know, when I think of a field, like you're saying, it's like you'd sort of imagine it as just a bunch of arrows invisible arrows that exist in space, you know? And those
Right.
arrows are there whether or not you put anything there to feel those effects. They're just, yeah.
And mathematically, you can define things about those arrows.
Yeah.
Yeah. And you can just define this EMF, this path thing, without actually having a wire or anything.
Okay.
So how many of the Morn problems for this chapter did you end up doing?
Only a couple. Only, what was it, 2? Did we do 2 last week?
Oh wait, I still have it up. Yeah, we've only met on this one, so we've done. Oh God, need to zoom out. We've done 2, and we're gonna meet one more time as a plan.
Oh, okay. So this 9.2 probably makes more sense to you then, given what we talked about today.
Did we do that one last week?
Yeah, it's the first one we did. So we took the divergence of the curl, but I think that wasn't quite right. So we have randomly.
I'm gonna hop off here, but
Okay.
I'll be in the chat. Are you gonna do one more day of this?
Yeah, next Saturday.
Okay, because I think it's good to like conceptually separate out displacement current and thinking about what it means, and then waves. And so, like, just doing a whole day of waves might be a good way to end it.
Okay, we can do that.
Hey,
right,
thanks, Dr. Cook. This is great.
Yeah, thank you so much.
Yeah, you guys are fun to work with. This is a lot of fun. All right.
Awesome.
All right, Don, I should probably let you go, right?
I guess we have gone over time. These problems are so much fun, though. But yeah, thank you for being here. Like for, I think every single one so far. So I really appreciate it.
I might have missed the first one. I don't remember.
Oh, maybe, but I don't know. Either way, thanks for being here for another week.
Yeah, thanks for always putting it on.
Yeah.
See you next time.
See you. Okay. Hey, Anders. All right, let me. I'm no good speaker, by the way. Hope you're doing well. So yeah, sorry, when we're doing this, it's a little bit hard to keep up with chat. So if I ignored anyone, it wasn't intentional. I'm just gonna take a minute to switch my title and category and stuff. And we'll do math for a little bit. feel a lot better about understanding what the displacement current is after that. Okay, there's that. Did I already get an image of this? I did. Okay. Hey, Joseph. No, I normally when I'm solo, I just use a program called Journal++. I don't normally use Excalidraw. I don't really. Me having that link displayed and random people hopping in is kind of an issue. So next time I'm not going to have the link displayed. Because I have been trolled like that before. Not with Excalidraw exactly, but I have been trolled with people drawing on stuff. So I can't allow that. For second meeting on chapter 9. Problems from Dr. Cook. Okay, posted the Excalidraw image. You're pointing out. Well, yeah, so I thought I was only putting the link in a place where only certain people could see it, but it turns out that you can just type in the thing on the top of the URL and anyone can join. Okay. Yeah, so I mean, it was too late for today already because it was really easy to rewind the VOD and just see what the link was. I would have had to make a new one. I didn't really feel like doing that, but I've absolutely had dicks drawn on my stream and stuff like that, so I don't want to. I shouldn't make a habit of that. Or at least like of making that link known. My title: Answering Math Questions. Chat. No. That in studying. Category math. Math. Speak Cooper, yeah. We've been doing electromagnetism on Saturdays. Today was the second to last one. The second to last like session. Getting ready for. Oh yeah, that'd be cool. Oh, let's see, my tablet is working at least with Journal++. I had to use my mouse because my tablet just would not cooperate with Excalidraw. Is it working with Journal? It's gonna be really annoying if it's not. It's lagging. Dude, frickin' Windows 11. I mean, it's lagging a lot less since No, it's lagging. I don't know how to fix that. I'm gonna have to do some Googling because this is hard to use. Wait, what? Oh, I made that undo. That's gross. Okay. You think you turned off Windows Ink? Oh, will that help? I don't know how to do that. Windows 11, Leon template. Oh God, okay, there's like a million steps that I'm seeing when I just Google it. All right, this will be It's kind of usable for journal plus plus, so I think maybe I'll just deal with it for now. What question was so? I was question from Anders. There's a good chance I can't do this. Find a closed formula that's not dependent on piecewise function. Return 0 for positive real numbers, 1 for negative reals. Oh. I mean, for anything like, so Anders put in a piecewise solution, which piecewise isn't acceptable, but I learned from Zach that there's this kind of cheesy. So, okay, let me copy the thing that Anders put. One half 1 minus x over x. But what if you had the square root of x squared over x? Huh? Huh? That's not piecewise. It's not simplified, but it's sure not piecewise. I mean, test values don't prove it. Well, 0 isn't valid here. And I mean, 0 isn't supposed to be valid either from my reading the problem. We're only asking about positives and negatives. But no, I mean, this just works. Like, we're counting absolute value as piecewise because usually I think absolute value is usually defined as a piecewise. Like that. But I think this is acceptable. I don't see what's wrong with that. I mean, you could also take. Oh my god, this freaking tablet. I don't know. Maybe it's not the best definition of absolute value, but you could also do that square root of x squared thing work. Yeah, I guess it depends how you're defining absolute value, but I mean, if that's the case, I think the first answer should be fine too. No, this is producing 0 or 1 for. It's not doing the second part, it's doing the first part. 8? No, 8 works. Um, I don't imagine there's a non absolute value answer for this. Not one that I can imagine. I mean, or I said non. If you have to do non-piecewise, I can't imagine another thing than square root of x squared. You could talk about floors or ceilings or something. Those are piecewise also. You're still not happy about it? I mean, it's not jumping, Cook. There is a cusp. But the desired output for the function also has it just has a jump. I don't know, how do you make a continuous function that describes a discontinuous behavior without something weird happening right out of discontinuity? I messed up the graph because I'm not good at math. Oh, sorry. I misread what you put. A Fourier series. Ooh, I like where you... Oh. I mean... Is that a thing that the Fourier series is like the Heaviside function? Because an infinite sum of sines and cosines, that's not piecewise. It's infinite, but it's not piecewise. Oh, what the hell? Two argument arctangent? What monstrosity is this? Huh, okay. A hyperfunction? Yeah, I mean, I think this is basically the Heaviside function. But, transformed a little bit. Hyperbolic tangent can approximate it? I mean, it's just, I assume Anders doesn't like that it's just ugly and not simplified. Which is completely fair. Oh wait, Fourier. A distribution? PV... What the hell is this? All right. What? What is the distribution in this sense of the word? Schwartz distributions? Oh. Makes the proof equally ugly as a piecewise. Okay, so it's one of those things where it's too hard to integrate it in this left form, so we basically make a symbol to represent this like integral function. Okay, so I guess the Fourier transform can technically help, but good luck using this. So I like that idea. Try the alternative one. Select the second one here. Direct delta is a distribution, not a function. Oh, really? Okay. Turns an even integer for any positive real number, odd integer for negative. Huh. I assume any, yeah, based on the phrasing. Like that the issue there is dealing with the decimal in a non-piecewise way. That would be better because you can make it mod 2, get the first one solved in a nice way. Old function plus 2 times new function. Because if you start with an even number, it's still even. But that's not accounting for any real number. That only works for integers, right? Oh, oh, oh. Oh! Wait. Like, you just use X for... No, maybe I don't understand what you're saying. What is old function and new function, I guess? Uh, I'm trying to like think of my own approach for this problem, and like really the biggest problem that I'm having is just at all trying to make a function that just turns a real number to an integer in the first place. Hmm. Coffee plus math equals endless energy times confusion squared. It finished. Hmm. Yeah, I. You're trying to get an isomorphism between groups. That's why you're doing this in the first place. I mean, the for function is also piecewise. I'm just kind of like googling this up to see if there's like an analytic version of these. Because floor, ceiling, and fractional all would be nice. But as they're normally defined, they're all pretty like piecewise. Oh, oh, you're just okay. I mean, it sounds like Anders is trying to do an algebra proof in that this one may meet the like, it doesn't actually help with the actual proof, or it has the same like difficulty apparently. Like, what happens when you mod a real number? It doesn't force you to give an integer, right? You can still get a decimal. Because if like mod doesn't work, then I don't know. I don't know what else. Decimals are not integers unless they end in 0. Unless you're responding to something else, Seth. Yeah, as Cook said, those are rational numbers. Hmm. Yeah, I'm sorry, Anders. I'm not sure I have an idea. This feels like an impossible question. I mean, there probably it is a way, but I just don't see it. Like, it's pretty difficult to represent something discontinuous in a continuous way like this. Yeah, I don't know. I think Penn said he'd be streaming tonight, but at least I don't see the way. Where did I leave off with this? Oh, you have a second one? Oh, that's right. What is it? Like, where is it posted? I'm reading it. Um, I was trying to read it, but I need to draw it. Just drew a boob. Better get the rest of the drawing before I get banned on Twitch. Touched by the circumference of circle A. P is touched by the center. Is that supposed to be circumference here? Otherwise, B has two centers, and that doesn't make sense. Okay. So just the area of two overlapping circles like this. I feel like I've seen this problem before. It's symmetric, so you want it to find half of it. No, yeah, the rotation shouldn't matter at all. Yeah, this is feeling pretty familiar now. I feel like Jed would just remember this offhand. I think there's a clever thing you can do with triangles. This is terrible. Oh my god, I can't. We know the distance from here to here is 5. We know the distance from here and also there. This is an equilateral triangle. Everything is 5s. Oh, maybe the problem I was thinking of was different. Yeah, I mean, I think this wouldn't be bad at all with polar coordinates. And doing an integral. I think there's a geometry way of doing this too that I'm trying to figure out. Yep, because it's the distance from P to the edge of the circle. That happens to also be Q, but, you know, that's how the problem is constructed. I'm sure there's a clever way of doing this. And I should turn a light on, it's getting dark. No, this is enough information to solve it. I'm trying to be clever in calculus. Calculus wouldn't be too bad though. I was hoping to find a way with just like high school geometry. I think there is one. I just don't know what it is. 1/6 of a circle minus equilateral triangle. Area of little cap on circular sector. Wait, okay. What does the 1/6 of a circle mean? Or like, where do you get that from? This is sacrilegious, but I'm sure I've seen a problem like this before. And it's bothering me that I don't remember. This is like the general solution. We have a lot of symmetry to work with, but I just want to see, like, it's probably too complicated. Oh. Oh, okay. I think I see the idea. I didn't look at all the math. But okay. So yeah, I think that's the way. Had a hexagonal graph paper, circle centers on 2 adjacent nodes, 2 nearest nodes. Huh. Yeah, if they're different radii, the problem is way harder, and I probably just wouldn't do it, to be honest. Because I tap out of problems when they get too hard. That's just the way that I am. All that crazy stuff with the Wolfram Alpha link, where you have to do... It'd be like way harder. This has a really nice trick because it's symmetric. The minute it gets not symmetric, you can't use this trick. The key here is to realize that, like, get the point of intersection here, and then just frickin' delete this circle for now. And the reason for doing that is that we know how to get the area of a sector of this circle right here on its own. In the area of this sector, we'll do blue, is that area right there. And you can do the exact same thing in reverse. With Q to P to get that area there. And the place where they overlap is that equilateral triangle. So as long as you don't double count that equilateral triangle, or like, you know, we have to subtract one of its areas out, we can get everything that's here. This guy does 2 hours. Okay, I had to find the problem interesting enough to want to go into a hard problem, I guess. Just like a normal geometry problem, I don't find that interesting enough, I guess. It's like there's a scale. It has to be at least as interesting as it is hard. Okay, so how do we find... We do need to find the angle, like that angle there. So the formula for what? Oh, for like the area of a sector? I think I know that. Oh, you know, we can find the angle using... No. Yes? No. Wait, my own drawing's confusing me. I have too many colors layered on top of each other. Oh my god, this tablet lag is driving me crazy. Okay, yeah, we can use trig to find the angle. So for that equilateral triangle, we basically want that angle there, theta, and that's gonna be the same angle as this angle over here. Theta, it's equilateral, 5, 5, 5, because there ain't no del. 5, 5, 5, 5, 5. Hey, Jed. Oh, you've been invoked by the geometry problem. What is it? Draw the chord between the intersections of the circles. Okay. Theta r squared over 2. Oh, duh, it's 60. Yeah, why am I doing trig? It's an equilateral triangle. It should just be 60. Thank you. I'm trying to do it the hard way. Do you have a separate idea here, Jed, with the chord? Um, 60 degrees in radians is pi over 3. So he said hex graph paper? Yeah. Chord will bisect PQ. Yep. The area of a sector, if you use radians, it's just r theta. Because of how radians are defined, I think. So that sector should just be 5 pi over 3. That's the Is it? Am I thinking of circumference? Oh, I'm thinking of arc length. Yeah. That isn't dimensionally right either. Yeah, Cook. You're right. It's over 2? Why is it over 2? Oh, because it goes to 2 pi radians? I don't know. I'm trusting Steph. Because I'm too lazy to Google it. Okay, so we've gotten the light blue area. Yeah, that's true. If I ever forget it, I could do a equals 0 to pi over 6, 0 to 5 RD theta, right? That's where the 1/2. Okay, yeah, fair. Okay, you convinced me. Oh, that's because a long time ago I was wondering how the theta looks like an actual theta on stream because I was trying to figure out if there's a way that we could get LaTeX on stream. And so as a test, I used 7TV, which is a browser extension that lets you do emotes outside of Twitch's control. Like it, so like on my end right now, that theta looks like an emote because I have the extension installed, whereas for you it just looks like text. And so I was curious about potentially trying to do one for every single Greek letter, so you don't have to do the copy pasting thing that PeachT just did. I don't know if it's actually going to be that helpful though, and you'd have to install a browser extension to see it for yourself, and it doesn't work on mobile. So I left the theta there because I was too lazy to remove it. But at one point I was planning to get an image for every single Greek letter and upload it to 7TV. I don't think it's really, I mean, I could still do it, but I don't think it's gonna be worth the time for the benefit that it would give. Yeah, Seth, I wouldn't worry about this thing. That's like a calc. Well, I think you might do it in calc 2. It's usually more of a calc 3 thing. I think calc 2 like barely touches on double integrals. I wouldn't worry about it though. It does touch on polar, I guess. But yeah, I just know the formula as you put it there in chat. Okay, so that's the area, that's like the light blue area that I shaded. We do need to figure out the area of the equilateral triangle. So we need to figure out the height. The height of that is 5 sine pi. What? I combined the s and the 5 into a 5. 5 sine pi over 3. Sine of pi over 3 is 3 over 2. Five n theta. Yeah, I'm really bad at how radians are derived. This should be 5 or 2 over 2, shouldn't it? Or no. Wait, we could do this with Pythagorean theorem also. It's not square root 50, I don't think, but it's... Oh, wait, is it? Oh, yeah, it is. Yeah, let me not use trig. Because this problem is way easier. Is that 75 over 4? Should be. Wait. Oh, this is 5 root 3 over 2. Ugh. Seth, I think you may have done the Pythagorean theorem with the wrong sides. One of the 5s is the hypotenuse. Oh, the bottom swell. Okay. And so that's the height of our triangle. So then the area of that bad boy is 1/2 full base times height. Please. 25√3/2. Okay. So what we're going to do, we're going to take the area of the sector, multiply it by 2, subtract out one of these triangles, and then multiply all that by 2. So let's have a 2 away on the outside. And what were the words that I just said? They sounded smart, right? We get 2 times 25π/6 for that. And then we subtract out one of those equilateral triangles. And then we simplify. I did call a triangle a bad boy, Casey Doodle. I don't know why I said your entire like Casey Doodle name, but like that triangle is a bad boy. I stand by that. This looks stupid, but I think that's the answer. You got full first names. Yeah, you messed up. I'm gonna invent a middle name for you. I mean, it can be one fraction, yeah. A dirty girl triangle. I mean, I want to say they call the single fraction simpler, but we can. Type it in the Discord? I mean, I can. Is there a reason to? Is that a negative number? It might be negative. I was planning to cook. I don't think I have anything else queued up. I think I did that part right. Area of triangles over 4. Oh, thank you, $10. Oh, I mean, that makes getting into one fraction even more annoying. But there's another 2 on the outside. That's where that comes from. I bet that's an even number. Even. Yeah, that's... If that's an even number, I would be amazed. I bet that's a positive number. Okay, well, I'm pretty sure I'm right here, but let me... Since, there's some discontent here. I'll do a little less mental math. So all I did in this step is cancel the 2 and the 6. And then now if we bring the 2 in, we do get 50π/3, yeah. 25√3/2. 30.7? What's the area of just one of the circles? Pi times 25. 78? All right, that seems reasonable. Less than half. This is ChatGPT doing the problem just for my sketch. Oh, it did it right. What the hell? So all Cook did was give ChatGPT a screenshot of the sketch that I made. This one before I drew the multiple colors on it. And it solved the problem, and it did it right. That's actually spooky. All right. Thanks for the problem, Seth. Sounds good. Okay. Where did I leave off? It's my potential ChatGPT. It's a messing with science, but all new tech is. Oh, hey, Speed Cooper. I don't know when you put that second yo, but hello? Yeah, AI definitely has crazy potential. Oh, okay. So I think where I left off in the blue book is I was looking at chapter 4, problem 22. I answered 22. I said it was a B. I was right for the wrong reasons, and I'm trying to revisit it and do it the right way. So I already know the answer is B here. And I think when I left off, I was in the middle of trying to justify the right way why it's B. You'd say it can do most undergrad math and physics problems now. Wow. Speedkeeper, what chapter is this? Or maybe I just answered your question, but this is from this book here. And it's from chapter 4. Yeah, so what I didn't realize about this book is that I was going through like the problems in order. Like I started with multiple choice problems, and then by the time I got to problem 22, I was super confused by it. And I looked at the solution, and it refers to problem 4.3 and maybe probably 4.5 also. And so I went back and solved these first 5, and now I'm revisiting at least these last few multiple choice questions, because I was completely lost on what to do for all of these last questions here. And I'm going to have to do that in the future, like do these foundational problems first, because doing them in order I don't think is a good idea. So I don't remember how I was thinking about this. Hey, Krim. It's been a minute. How are you doing? I want to delete this. Let's have a fresh view. It has been a hot minute. You're good? That's good to hear. I want to take a bigger screenshot of these pulleys. That's too big of a screenshot of these pulleys. Okay, so if this mass here goes up by A3 over 2, this side over here goes down A3 over 2. Big boys, bad boys, dirty girls. There's many boys and girls here with varying qualities. um, so yeah, if A3 goes up, I do expect these two to go down because of what I just said. So we expect our result to have a minus sign, but would you look at that? They all have minus signs. So that doesn't help eliminate possible answers, but it does dirty girls in their role play. Oh my god. So there was a weird thing where I was kind of thinking of A1 and A2 as being like kind of like localized, but I think they're not. Like I was mentioning A1 and A2 to only care about this scenario here without anything else, but that's not how you think of them, I think. I think you have to think of the net acceleration, not just in this one like subsystem or whatever you would call it. They might individually, like if one side is heavier than the other, that you might get some individual like movement between them, but on the whole they should be both going up or down because of this A3 situation up here. The SVQ, it's simply conservation of string. Okay, so maybe instead of accelerations, we should maybe take Dr. Cook's advice and think about position rather than acceleration. So if we just take the third mass and put it up by a distance h, we do expect the other two masses to go down by h over 2. And how does it look as an equation? Like I was about to say, like a displacement. This isn't quite right. This is definitely not right. I want to make some relationship like this though, and then take the derivative twice and call it acceleration and call it good. An error-proof method of these questions is a virtual work method, more procedural. Like, is it a good way to do it or a bad way to do it? You said error-proof. Good way? Okay. Question gets solved quick. Okay. I'll look at them in a second. Google 7MDY. How do people love math, man? It's a fair question. I think we're all just a little bit crazy, to be honest. That's the answer. Welcome in, and thank you for the follow. What if I Google virtual work method? Curious to see more. This might be in a different context. And this is beyond what this chapter of the textbook would expect us to know. Like, we haven't talked about work at all yet. So I would want to do it the conservation of string way, but this is interesting too. Where's the virtual work part come in? Okay, this might be a little bit too much reading that I can really do right now. All right, as soon as you know that it exists, but I think I'm gonna not try to learn a whole new thing on stream right now. Yeah, how the hell does this work? The answer is seriously B. I feel like it should be C. I'm pretty sure the answer is B, but like I can see rationalization for C. I can't see one for B. Um, But everyone's attached to them, a set of variables to measure the position of each point from the fixed top. There are probably nicer shortcuts. Yeah, I feel kind of weirded out because there's like, I feel like there's competing things happening here where A1 and A2 should kind of have their own thing locally going on with just each other. But then this entire block as a whole interacts almost as one piece with A3. And I don't know how to like, it's weird that those two, that you can write just one equation to describe the situation, which is what this question seems to do. So if you measure it from the top of the ceiling, I mean, this pulley up here is always stationary. It's just anchored. This pulley here would go down by h over 2. Which means this pulley here would also go down by h over 2. And so each of these masses would go down by h over 2. And that's where I think, like, that, like, I keep going back to, it's like, you know, some displacement of the third mass should be like this, opposite direction, then each of them is the other two displacements cut in half. But this just isn't right. That's why I'm stuck right now. Next, you also have to consider moving A1 or A2 a little also. I guess so. Is that where we need number 5? Like we need to think about this thing. But this is just like, it's just introducing so many other like constants and things that weren't in the problem that I'm kind of hesitant, but like, or like, I can never talk about masses or forces, which is why I don't like involving 5, but like, if we're allowed to only think about just that pulley on the bottom, it would just be like y1 equals minus y2. If a1 goes up, a2 goes down. But if these are both true at the same time, then the answer would be E, or not E, not even E. It wouldn't be an available answer. We do no need to bring math or force. Okay. Hmm. There's something more complicated going on here. Like, I just feel like A1 and A2 are, if we move A1 up or down, how are we possibly affecting A3, everything else being equal? I feel like we're just not. Imagine A1 and A2 both drop, then A3 will go up. Okay, yeah, so if I yank on both A1 and A2 at the same time, I guess I didn't realize that was a valid thing that we could do. I only imagine moving one of the masses at a time, but yeah, why not? If I yank them both down, is that not just the reverse of the situation that I was just doing with A3 going up? Like, I thought that's what I basically did when I considered moving A3 up by a distance h. Am I misremembering the solution? Like, I thought I checked the answer and it was B. I thought I checked it twice. Is it C? I went into, okay. But, I mean, I feel like I've considered when they're going in the same direction, and the other thing left to look at is when A1 and A2 are opposite directions. That doesn't seem to be very helpful. Changing the average height of M1 and M1 to M3. If M3 is fixed, M1 and M2 have to keep the same average height. Right. Any change in average height for M1, M2 comes from N3 moving. Yes. Oh. Is that why we... Wait. Okay, so... This is, if we had a terribly drawn system that was nearly like the one we just had, except we have like an average mass, like maybe MA for average, and that's our good old M3. I'm mixing M's and Y's. Y3. I see the chat is moving. I'm just going to think this through for a second more, and then I'll look at chat. A change in Y3 would produce a change in the average thing, it would be half minus y sub a over 2. But then the average, we can calculate, well, this is getting over 4. That can't be right. I should be getting a cancellation. Okay, I'm looking at chat. Delta h1 plus h2 over 2. If there's a change in the average height to minus... You did special cases. Oh, really? Oh, I did reverse it. It should be, yeah. Well, yeah. Y3 is more than YA. That does get the right answer, so that's also how I'm justifying it. I think, oh my god, have I just been flipping the fractions this entire time? Y3 should be twice as much as YA here. Oh my god. Okay, that's so much. Oh my, dude, if I realized that, I think I would have solved this problem so much faster. I was literally just flipping it. Okay. I think I get it now. I mean, yeah, no, never mind. Change in average height of 1, 2 equals change in height of middle of the pole equals negative change in height of 3 over 2. I think I did the same thing in with a different phrasing. I think drawing it like this as a separate system and just getting rid of y1 and y2 is what I needed to see, to be honest. And also not, like, realizing that the relationship is this and not with 1/2. Okay. Get rid of that. All right, 23. And okay, can I say whoever Atwood is sucks? Stupid person, stupid machine. Hate it. All right. Conservation of stringulation for Atwood's machine shown up here at 4.12. All exceptions. Ugh. Okay, yeah, this is the one where I just like... I remember this one. I just gave up on this one and said, I'm going to go do the foundational problems 1 through 5. Curse in the House of Atwood. That sounds like the name of a Game of Thrones spinoff. Harambe. It's been a minute since I've seen you around. You're calling it E? Could be. Okay. If A3 goes up, A2 goes the opposite direction, and then we have a 2 in front, not a 1/2, because A3 is twice as big as A2. And then if A2, you know what, maybe this will, I should maybe use H's here to help track. H. That's not proportional at all. H over 2. I'm expecting this one to be H over 4. Agree, and it should be. Ooh, I don't know how I feel about this. Yeah, no, I hadn't gotten to the accounting for M1 yet. And I'm not saying this is right as I wrote it right here. Yeah. Means E gets attention in A3 goes throughout the pulley system. Yeah, like all 3 terms should be involved here. Bottom 2 pulleys being pulled by 4A3. Also being pulled up by A1 and A2. Wait. If I yank it, A2 goes up, which gives slack to A1, does it not? Maybe I should imagine moving A1. If I yank on A1, A2 goes up, and that gives slack to A3. Now, why am I obviously wrong and everything has the same sign over here? Hey, Joy Deep. That happens. Okay, if I pull on A2, what happens? If I pull A2 down, A1 and A3 should both go up, right? Why does everything agree with each other? Wait. No. Moving only 2 masses at a time? Give me the acceleration. I think you're only looking at the masses applying external force, and so we can just give you the acceleration of the masses. Fix 1 mass, move the other 2. Okay. If we fix M1, we would find that A3 is equal to minus 2A2. We fix M2. Is equal to minus 4A1? Is that right? I guess so. Hey, Seon Yoon, polar questions? Yeah, it depends on the question. There's some hard polar questions out there, but if you have one, feel free to give it to me. Am I a teacher? No, I've been a tutor. But I'm not an official like teacher. No. Conservation string means there necessarily be a linear relationship between A1, A2, A3. Relationship can always be determined by considering only two variables, non-zero at a time. The constant should be flopped. I that's how I used to do it, and then I wasn't getting the right answer. A3 is twice as much as A2. That's how I'm thinking about it. If we have M3 fixed, my M2 fixed scenario was not right. Oh, yeah, it should just be a -2. Because if M2 is fixed, it's not actually, we're not getting this progression. Yeah, A2 is not, if M2 is fixed, it's not taking up any of the string. Okay, yeah. Is fixed M1 like the last question? Fixed M1 is maybe, yeah, like the thing that I drew right there is more or less what fixed M1 is, I think. Okay, if we have M3 fixed, what happens here? Ooh, you're doing an arc length and polar coordinates, Ian? I should be able to do that. If you don't mind, just give me a few minutes to hopefully finish this problem. I can look up the formula for that, and I should be able to work it out. Awesome. If we yank A1 down by a distance h, A2, I'm getting H5 still. I feel like it shouldn't change. Maybe, no. There's a double? No, I think it's just H. I'm trying to think about, like, this string over here is anchored, so only this string is moving. And then over here, like, this string is anchored because A3 is fixed, so only that string is moving. So I think they're one-to-one in that way. Opposite directions, but once you've worked out the third scenario, you can solve like this: K1, A1, K2, A2, K2, K3, A3 equals 0. Use the case where he did. That feels like something that Purcell did with capacitance constants. I don't remember the exact thing. In like superposition. So if A1 equals 0, measure between voltages and charges. Okay. K2 A2 minus 2 K3 A2 equals 0. A2. Wait, I'm solving for K here, aren't I? Or I'm solving for the K's. I need more room. If A2 equals 0, then K1 A1 minus 2 K3 A1 equals 0. And if A3 equals 0, K1 A1 minus K2 A1 equals 0. Oh, you can divide them out. Okay, yeah. So you don't care about A2 equals 0. That makes life a lot easier. All right, you know what? I want to look at Sion's problem. So I'm sorry to like keep this in suspense, but it's going to take a minute to work out a system of equations like that, and I would rather help someone I was asking for help. I know, but it's simple from here, I think. And I feel bad making someone wait. There's an actual question. That's the point of the stream. Oh, okay, that's a nice formula. It's not a full system? Okay. Oh, shoot, I wasn't showing my thing. I'll drop you a link to this page, my favorite calculus website, Sion. And they have a page on this exact thing. So let's go and work out your problem. I know, Casey. Ah. Streaming is hard, okay? Okay. Is there a channel to upload on Discord? Yeah, Harambe, if it's like a general like math thing, like math discussion or math homework help. Or I mean like for like math discussion, you're trying to like contribute to a problem that I'm doing. Okay, so L is equal to integral, just trying to copy down the formula from Paul, root r squared plus dr d theta squared d theta. Okay, so once we know this formula, it's really just kind of plugging things in. But let's go ahead and do that. So we already know that r is equal to 10 over 1 plus cosine theta. That was giving us in the problem. We need to work out what dr d theta is, so let's do that. Dr d theta, that is annoying. I'm going to rewrite it as 10 times 1 plus cosine theta to the negative 1 prime. You don't have to do this, but I think it makes it, the next step a little bit easier to look at. I have not actually taken the derivative yet. Actually, instead of prime, I would rather have d by d theta, I think. And so now when we go to actually take the derivative, it's a little bit more clear to me what to do because that -1 is just helpful for me to see for the power rule. So this 10 is a constant coefficient. It can stay out in front. I'm going to apply the power rule to that -1. So the negative comes out front times 1 plus cosine theta, just whatever is inside. And then now we subtract 1 from the exponent, -2. And now chain rule, multiply by the derivative of the inside. So 1 plus cosine theta, the derivative of that is negative sine theta. And now the only task is to clean up. So we do have two negatives multiplied, so it becomes positive. I'll put the sine theta out front, times 1 plus cosine theta, it's a -2. And now I'm going to get rid of the negative exponent again because it looks ugly otherwise. 1 plus cosine theta squared. Okay. We have all the pieces of the puzzle we need now, so let's go ahead and plug into the formula. L is equal to the integral. They give us the bounds. They're kind of nice like that. Theta is 0 to pi over 2. We're going to have a big old square root, many things inside it. R is that same function that we just worked with, 10 over 1 plus cosine theta. Oh, this is going to be an ugly integral, isn't it? Squared. Oh, no. Plus drd theta squared. So the thing we just found, put in parentheses and square it. Wow. Let's hope we get some cancellations here. All right. We might. First thing I'm going to do is, with these fractions that are squared, I'm going to make it the top squared over the bottom squared. One plus cosine theta to the 4th on the bottom there. I think it'll clean up. I don't think this will be the worst thing in the world. Okay, I'm going to factor some things out. 0 to pi over 2. So anything that I'm concerned, actually, I'm just going to show you what I'm going to do. I think it'll be more clear once you see it. I'm going to factor out a 10 squared from the top and a 1 plus cosine theta squared from the bottom. And everything that's left over will go in big old brackets here. We get a 1 for that first term. And we get a sine squared theta over 1 plus cosine theta squared, close brackets. D theta. Okay. And I did that because we can use exponent rules to simplify the left part a little bit. If you have the square root of two things multiplied, like if you have root of 2 times 5, you can rewrite it as root 2 times root 5. And that's convenient here because each of these two things are squared. So there's going to be a cancellation. So that first term, I'm going to give its own square root. And the second term, or factor, technically gets its own square root. Who cares about the terminology though? Oh. This doesn't simplify how I hoped it would on the right, but there's still hope. Okay. Now, these two squareds will cancel the square root on the outside. Hey, Lee. So we end up with just 10 over 1 plus cosine theta, and that's all on the left. On the right, we have the same ugly thing. Yeah, surely. Go for it. Now what the hell do we do with this? I thought I had an idea for how I could deal with this thing over here, but it doesn't work how I hoped. Yeah, see, and this is not an easy integral. Sorry, I should have checked if you were here before. Were you here for when I set this up? Because if you stepped away for a minute, this would be even more confusing than it already is. Yes? Okay. Good. You were here? Okay, good, good, good. What the hell? A common denominator might help? Okay, you know what? Because I don't feel like writing out the entire integral every single time. I just want to do some side work. Just working on this little piece inside the square root. So I just want to play around with this little piece here and then return to the problem at hand. Yeah, Krim, this is a question someone asked, so I want to work it out for him. It's the arc length of a polar function here. And it's much messier than I thought it would be. So I'm going to get this one and turn it and get it a common denominator. And hope for the best. I'm really spitballing here. So I'm gonna put these into one fraction now they have a common denominator. At the same time, I'm gonna multiply out that squared. So we get 1 plus 2 cosine theta plus cosine squared theta plus sine. Oh, hey! I think this does help. Sounds good, Lee. Polar function once again. Yeah, I won't be able to like stay on it, but if you can like take a screenshot of it or something. There's the original problem again. How does precession occur in a gyroscope? I have no clue, to be honest. Sounds good, Krim. Thank you. Okay, cosine squared plus sine squared is 1, thankfully. That's the Pythagorean identity. So 1 plus 2 cosine theta plus 1. And now we are going to get a little bit of a cancellation. Because 1 plus 1 is 2, last I checked. And we factor a 2 out from the top. And look at that. We're going to get a partial cancellation here. So we get just 2 over 1 plus cosine theta. Lee, I'll take a look at it after I'm done with this problem. Okay. What this means is we can come back to the integral problem, and instead of this thing here inside the square root, we can plug in the thing that we just found. So maybe I'll even copy and paste. Excuse me. Thank you. And instead of that thing, you have 2 over 1 plus cosine theta. Okay. Well, if we do more exponent magic, I notice we have a 1 plus cosine theta here and a root 1 plus cosine theta here. So we could rewrite this as 10 root 2 over 1 plus cosine theta to the 3 over 2, which is still terrible. Let me see if Wolfram Alpha is let me consult my buddy who's an expert on integrating random shit that I don't immediately see a solution to. I hope it's not a virus stress sub. That would be a lot. Oh no. You hate to see it. Oh my god. That turns into the integral of secant cubed. That is a neat idea with the half angle. This is a crazy problem, Cian. God, I haven't like messed something up early on in the problem, right? Is my derivative okay? I think so. It's a polar arc length integral, Anders. Okay, you know what? Maybe I'll give Wolfram Alpha the original integral, like right there, and just make sure I didn't miss something easy off the bat. I don't think I did, but it'd be nice to have this number as well, just for the sake of being able to verify whatever I do eventually get. Turning back to rectangular, that turned out to be a nightmare too. I've had to do the integral of secant cubed a couple times to the point where I feel like I shouldn't. What? No, you can't do this to me, Wolfram. You can't tell me it's inverse hyperbolic tangent and tell me you don't have a step-by-step. That means it's something really simple. I think I'm missing something. I didn't see another way, Harambe. Is there an easier way? Inverse hyperbolic tangent, bro. There's another, you know what? No. Let me try integral calculator. I'm pretty sure. I feel like I showed how you can. 10 over 1 plus cosine x squared plus 10 sine x over 1 plus cosine x squared go. Okay, that seems approximately what... Wait. What? Let me plug in the balance. Wait. 11.47. It does get the same answer. Yeah, they say it's a parabolic segment. Go back to my work? All right. Like, maybe it's better to keep it combined, but I don't think I did anything invalid by splitting up the square root. Lizzie, I'm sorry to hear you failed your final. That sucks. A tangent problem, but with 4 different points. I don't really think that problem f of x equals x cubed, some bullshit of a building tangent line with 2 points, but they don't cross each other. Yeah, I mean, it's hard to solve a problem when you only remember a part of it, but I'm sorry to hear about your final. There's always some really weird questions they can ask you where, like, they ask you for the tangent line through a point, but the point isn't on the curve, and you have to do some crazy stuff there. I hope they're able to, like, retake it. I don't think the integral of secant cubed... I think it is annoying. I know that I've done it. I know that I've, like... I used to just remember it by heart, because it came up, like, so many times in the same, like, 2-week period on the stream. Oh, I think you do integration by parts. I don't think you do the weird thing Wolfram Alpha's doing. But yeah, Rombe, if you want to keep on looking at this, just take a screenshot of it or something, because I want to scroll around and keep working on this. Oh yeah, it is like the type of problem that I thought. Secant cubed, you could call it standard. It's not what I would expect. A normal like calculus to know though. Okay. Okay. Sorry, I'm debating what I want to do here. So Lee put a question in before, and it's a really quick one. Because this problem, like, I think we have the right setup. It's just doing the actual integral takes a long time. And this is like a lot of progress, but there's still a long way to go. So, Cian, if you don't mind, I'm going to take a little break from this problem. I will come back to it and get the actual answer. I think what I've done for the setup here is correct, and it's just a matter of following through. But actually following through is really annoying. Okay, I will try. I will come back to it though. Sorry about that. I just don't want to keep other people waiting. And let's see. I'm just gonna do this quick triangle one, and then I'll look at yours. So this is from Lee earlier in chat. Looks like this is a trig problem. So we want the length of this segment here. We don't know that, but we can get the length of this segment here, I see. No, Cook, there's questions. No, I've been working on that one the entire time. We know that sine of 26 degrees is equal to opposite BD over hypotenuse 22.9. So then that means BD is equal to 22.9 sine of 26. And using a calculator, so I assume we're supposed to do that here. 22.9 sine of 26 in degrees, 10. Oops. And now since we want BC, I think we can use sine again, as it turns out. Sine of 49 is equal to opposite 10 over BC. So then that means if we rearrange it, well, okay, let me do this in two steps. I'm going to multiply each side by BC. And then I'll divide each side by sine of 40. And then that's a calculator. 10 divided by sine of 40. 15.6. Oh, they said to the, I should be putting 0.0 because it said to the nearest tenth. I forgot what number I said. 15.6. Okay, let me take a, I'm not sure if Lee is still here, so let me take a screenshot of this work. And send it to them in Discord. Oh, law of sines, could you use it there? Yeah, you probably could. Okay. And hey, I forgot how to pronounce that. Yoako? Okay, let me do Lizzie's problem here, and then I'll come back to Cian's. Triangles have a radius? Oh, you're talking about that one? Yeah, I don't know what that means. Sorry, I'm trying to like catch up on the problems. Yeah, the problem was asking here really is that y equals x cubed. Oh, please don't bring politics into this. Y equals x cubed looks like this. And the point 40 is somewhere over here. And so we can imagine there's a tangent line. Somewhere like that. I'm drawing it terribly. And then somewhere like way up here, I think, is what I expect the tangent lines to be like that go through that point. And how you think about these problems is, you remember that y equals x cubed, and then y prime is 3x squared. And so we have to remember that the derivative is the slope of the tangent. And we're asking about the slope through a point. So, oh my God. The slope of a line in general is m is equal to y1 minus y2 over x1 minus x2. And we know that one of the points is 4, 0. It doesn't matter which one we choose as long as we're consistent. So I'll make 4, 0 the second point. Why not? And I'm even going to drop the subscripts here. Y minus 0 over x minus 4. And actually, not only that, but we know that m is the slope. And we also know the slope is 3x squared. So it's a really weird thing with these problems. Like I had to look up the solution to a problem like this when I first saw this type of problem. The other thing we know is that y is x cubed. So we can plug that in up top, and minus 0 doesn't do anything. Now we have an equation we can just solve for x, and we should get two solutions. But that's kind of like the idea of this. And I'm sorry that I'm kind of like speeding through it, but if you need me to re-explain a part, please like let me know. But there's a couple of questions at once. I try to help everyone out as quickly as I can. So we subtract the x cubed over, and we get 2x cubed minus 12x squared equals 0. Divide each side by 2. X cubed minus 6x squared equals 0. Factor in x squared out. X minus 6 equals 0. Oh, duh. Actually, is that duh? No, I don't know. One of the solutions we get is that x equals 0. The other one is that x equals 6. Sensor, can you explain every part? Oh, yeah? Iwako? No, I'm not an engineer. No. I'm American. This comma is just a separator. There is one solution with x equals 0. There's another solution with x equals 6. It's not 0.6. Sorry. I forgot. That's a weird... other countries use a different convention. Okay, so they want the equation of each of the two lines. We've done the hard part. The more annoying part is finding what y values pair with each of these x values, and then getting the slope, and then finding the equation of the line. You recognize the equation for gradient? I mean, I use a derivative, or I don't know. Like, is that how you? I don't know. So if x equals 0 and y equals x cubed, then y equals 0. So one of the points is 0, 0. If x equals 6, then y equals, oh god, 6 cubed. Who the hell knows what 6 cubed is? 36 times 6. That's a job for Wolfram Alpha. 6 cubed. 216. The other point is 6, 216. Okay. Yeah, Lizzie, this question has a lot of like tedious work, but we're nearly there. So we basically have to find the equation of the line that goes through the origin and 4, 0, which I mean, that one's straightforward at least. That one's just y equals 0. The other one, we have to find the equation of the line that goes through 4, 0 and 6, 216 way the hell up here. Oh, yeah, m. Slope, yeah. Sorry, we usually call that slope, but gradient is also a fine word. So the first one that goes through these points, I would just say y equals 0, which is a flat line. A horizontal line is always y equals something, and it's right at 0. So y equals 0 is one of our answers. Box it, ship it, send it home. The other answer is, there's a couple ways. If you have 2 points and find the line between them, there's a couple of ways you can do that. We have to find the slope of that line first. Ugh. M is equal to 216 minus 0 over 6 minus 4. Basically, the same equation we did here. Sorry, I'm using this equation up here, but we can actually know what y and x are now. So it's 216 over 2, and that's 108. CU? I never said CU. Felipe, can you make the infinite string using UML integration? I'm sorry, I don't know what that means. Oh, no worries. You're just like clicking things. So that's the slope of the line. If we use point slope form, you could say that y minus either of the points. I'm going to use the simpler point 0, 4. Y minus 0 equals slope times x minus 4. And just simplify that. 108x minus 4 times 108, 432. That's your other answer. Box it, ship it. So yeah, that's how you do that one, Lizzie. It's not an easy problem if you haven't seen it before. Like, realizing that you have to do this fucked up thing is super weird. Don't ship it to Canada. Yeah, I'm sorry to hear about your final, but I hope that helps a bit. Okay. I guess we're back to the polar integration problem. Wolfram cleverly used a half-angle identity here. Oh, I shouldn't have closed that tab. Ah! Frick. I lost my integral calculator tab. Cosine 2 theta equals 2 cosine squared minus 1. I think it used this identity. Yeah, it did. Okay. So add 1 to the other side. 1 plus cosine 2 theta equals 2 cosine squared theta. Tangent x over 2 substitute help. It probably could, but I think I know. I think there's a simpler way. It was simpler is relative, but now if we can cut theta in half, we would get 1 plus cosine theta equals 2 cosine squared theta over 2. And now 1 plus cosine theta matches with the problem. The 10 root 2 can come out front. Let's do that. And we end up with 2 cosine squared theta over 2 to the 3 over 2 d theta. All right. 10 root 2. I'm going to bring that 2 gets a power of 3 over 2 and it comes out front. And then cosine squared to the 3 over 2 becomes cosine cubed, and 1 over cosine cubed is secant cubed. Okay. And integrating secant cubed is annoying. I think you do integration by parts. I want to derive a secant theta over 2, and I want to integrate a secant squared. Secant theta over 2, tangent theta over 2. V is tangent theta over 2. How does root 2 divided by the exponents subtract? 1/2 minus 3 over 2. It's just -1. Okay. So we get 10 over 2, which is just 5. That's a nice number. Inside integration by parts, uv minus v du. Okay, how do we integrate secant tangent squared? Oh, that's not as easy as I thought it'd be. Oh, is it one of those? Oh, do we have to do integration by parts a second time? How does that Pythagorean identity work? We want secant, so we want to divide by cosine. Okay, so secant theta over 2. Tangent squared is secant squared minus 1. And then we get secant cubed again, and I think that's okay. I'm even going to split up into 2 separate integrals here. Drop my bounds. And that's because this entire thing was equal to that integral, and we have that same integral again. So we can add it to the other side and divide by 2. Can we just ignore the 5 and the 10 root 2 business? I think we can. I think the moral of the story... Well, yeah, but I think we just add it to the side, Fembox. I think we're okay. I think this thing goes away and we just divide by 2. That's what I'm saying. So 5 over 2 secant theta over 2 tangent theta. Oh my god, bro. The integral of secant, I'm going to say we can look up. I'm going to make that executive decision there. That's secant x. Oh no, I don't need to look this up. It's secant ln secant plus tangent. Chain rule 2. We have to multiply by 2? Is that it? Yeah. How does that feel? Do I need the 2 out front? I just need to write that out because I can't visualize it right now. Yes, we do need it out front. Okay. Hopefully, okay, just plug and balance and I think we're okay. Let's pray. Thankfully, the bounds are relatively simple. Oh, they're about to not be. Secant pi over 4 is root 2. Tangent pi over 4 is 1. Root 2 plus 1 minus secant of 0 is 1. Tangent of 0 is undefined? No. Is 0? I hope. Tangent of 0 is 0. That sounds right. Okay, good. So we just get a big old 0 on the right. Please tell me that this matches the final answer. I would be a happy boy. If this is 11 point whatever. 11.478 is what we're hoping for. Cross your fingies, your toes. 5 over 2, square root 2, plus 2, ln, root 2 plus 1. No! 7.9? Oh, wait, you really? Going back to rectangular? Wait, what's the definition of inverse hyperbolic tangent? Because I just noticed, like, what I have matches that almost exactly. 5 root 2 Give me a simpler one, please. What about the inverses? I don't get it. The article is for inverse hyperbolic functions, but there's no inverse on these. I don't trust that. It should be an ln. Oh, wait, it's a. Wait. Oh, my God. Okay, they're saying a tan, or r tan. Okay. Ugh. ln 1 plus x over 1 minus x. Because I'm just like... I think the mistake is somewhere here. Everything else seems okay. One half ln. Ugh. One plus x over 1 minus x. Hey, Zach. I like your polar integral so much that I'm just doing the most disgusting polar arc length problem. It's 3 pages of pure integration. Hope you're doing well, dude. I got an answer, but it's very slightly off. And I'm trying to figure out why. Arctan. So Wolfram Alpha is saying I shouldn't be having arctanch 1 over root 2, I think. And so what does that look like in the formula? Okay, now let's simplify this. And if we rationalize, I assume the denominator. Two plus 2 root 2 plus 1. 2 minus 1. 1 half ln 3 plus 2 root 2. Which is slightly different from root 2 plus 1. Did I do the UV right in the sense of constants? Oh my god. I sure didn't. That's an amazing catch, Harambe. Well, there's your problem. I didn't do chain rule. Or the U sub. There's a 2 there. Okay. Well, so that means there's a 2 out front there. But the constants still cancel over here. Like 2 times 1/2. We just get 1. So let's update that 2 for sure. And then let's see. Where that gets us. Oh my god, it matches. Okay, we did it. Great call, Harambe. Okay, yeah, see, and so apparently, Lubert is saying that it's slightly easier in Cartesian coordinates if you just convert it. But you still have to contend with the integral of secant cubed. It doesn't seem like there's a way around that. But some of the stuff that I did early on here with factoring square roots, you could have avoided, I guess. Oh, did my thing actually match their crim? Okay. And Joel, what is Calculus 3 all about? The quickest way to describe... Oh, shoot, I'm not showing the journal. The quickest way to describe Calc 3 is that it's Calc 1 in 3 dimensions. You extend the things you've already learned into multiple dimensions. The integral of secant cubed, my nemesis, yeah. So what I was saying is that you could have avoided some of this stuff apparently by converting to Cartesian, but you still end up with that bad boy. So that's a doozy of a problem. Yeah, that... Like, I feel like the goal of the problem, we already answered here. Like, we set up the correct thing. It's just a matter of getting the number that, you know, a computer can do that for you. But if I was your teacher, I would care way more that you can do this than actually execute that integral. But you might have to do that in your class, so I'm sorry if you do. Imagine being ugly at all coordinate systems. Ugh, true. We need a new parabolic coordinate system. No worries, Cian. Thank you for the question. Yeah, I feel like there should be some kind of like closed, like someone would have figured out a general formula for the arc length of a parabola. Oh, thank you, Cian. I'm sorry, I'm probably pronouncing your name wrong, but I hope I'm close enough. Okay, maybe we'll finish up that one Atwood's problem. I mean, that's right? Awesome. With the pronunciation? Okay. Maybe we'll finish off 23 and call it a day here. Yeah, like, I don't think I have ever learned about the hyperbolic trig functions in any of my classes. And it feels like there's some situations where they're definitely helpful. Can I move this page up? Or I can do insert page after. Aha! Want to buy some hyperbolics, Fizzbuzz? Ugh. My teachers warned me that people would come up to me and offer me free hyperbolic functions, and I should always say no. Which I feel like I'm missing out on the free drugs if that is true, but it's neither here nor there. 2k3 equals 0. That's a minus. So I'm taking these equations here and removing the a's and solving it for k. K1 minus 2k3 equals 0. K1 minus K2 equals 0. Well, don't tell me you got it from me. All right, now we have annoying. K1 equals K2. Ugh. So that means K1 minus 2K3 equals 0 at the same time as K1 minus 2K3. Well, that's not. What? Did I copy something down wrong? No, that's okay. We only care about the coefficients between them, right? So I think that means if we put everything in terms of K3, 2K3, A1 plus 2K3, A2. What the hell are you doing, tablet? Stop! What? Stop! Bad What? Okay. Are we cool? Okay, thank you. Dude. Zach, ever since I updated to Windows 11, everything has gone to hell. I'm gonna switch to Linux. I'm gonna get a chalkboard. You know, I'm converted. Exactly. So 2A1 plus 2A2 plus A3 equals 0. A3 equals minus 2A1 minus 2A2. Please tell me that is an answer that's provided and the correct one. It is a provided answer. Let's check the answer key. Okay, 23. Don't scroll down too far. B? I said it was B? Oh my god, I did it. I just spoiled myself on 24. I scrolled too far. Okay. Hopefully I'll forget it the next time I do this. The left mask goes up by Y1. There's 2Y1 less string up. I should learn that intuitively. The left mask goes up by Y1. There's 2Y1 string segments above it. That's a way easier way to do it. Okay. We're calling the stream. My tablet is only working half the time. Okay. I'm gonna have the YouTube stream off here, so if you're on YouTube, thank you for being here. Be back at some point. Oh, a Minesweeper? Oh, you snuck that one in. All right. We'll do a Minesweeper. How difficult sounds problem to you drive the equation in motion of a skydiver with the parachute is open? Depends how accurate you want to be. The equation for motion with air resistance is not too bad at all as a differential equation. If you can neglect the surface area of the parachuter, I think just the parachute itself is probably not that bad. I imagine, at least. Oh, RNG. Okay. We got good RNG. Bam. Don sweeps mines. Yeah, I'm thinking about becoming a professional Minesweeper player. I got good RNG there. Normally it takes me a few attempts. Because you just there's sometimes you just have a 50-50 shot or a like a 1/3 chance. Oh, another one? Alright. Let's see if we can get the twofer. Ah, my fingers are cold. Ah, this is RNG Island up here. Ah, okay, we're good. Fuck! I clicked the wrong one. I meant to click the one above it. That's cold fingers. I take no responsibility. Um, RNG. Not full RNG. No, it's not RNG. Okay, there we go. 44. What is this? Oh no, Anders? Mega Minesweeper? Is this gonna be a massive one? Oh, it's not loading. Oh. Oh, hexagon? Oh no. I don't know how this works. I wasn't prepared for this. Reload to start over? Oh my god. Oh, I see. You can choose a... Oh my god. Triangular Minesweeper? That's hilarious. Oh, this hurts my brain. Wait. Did I lose? Or is that free? I can't tell. I don't know what to do. Yeah, I don't know what the adjacency means. I assume I lost. No? Oh, you get multiple chances? I don't know. Oh. Well, you... okay, yeah, it's the honor system. Okay, that's funny, but it hurts my brain. I can't do that one. I'll do a normal one, so, like, you know... That's what I promised for your 1,000 points. That one hurts my brain. Fuck. There's a... Yeah, you're right. I don't. If I do one that's too big though, I'm gonna be here for a while. All right, slow down. Don't misclick. I just want to go fast though. I was born for speed. Wait. I didn't get every last one. I needed to click that one and then maybe also that one. Why did it say I won? I'll take it. Oh, because they were empty, I guess? Okay. Yeah, points for 50 more? Oh my god. A Rubik's Cube? Oh my god. Oh, you guys are... I joked about keeping Zach on for 24 hours. Now that it's being turned around on me. Alright, I'm not going to do the scramble what's on there. I'm just going to do a random scramble. Alright, I'm not solving yet. Alright. Inspection. Okay. Oh, my fingers. Oh, this sucks. Oh. This is so much worse than Minesweeper. Oh, I did it wrong. Oh, it's gonna be a terrible solve. You know, R perm. Who even likes those? Yeah. Pretty poopy. Abstract algebra in the real world. That book that Penn Center's been using does use a like it does use a Rubik's Cube for the permutation groups. All right, and this is the Minesweeper that Phobos redeemed. Oh, RNG? Yeah, okay, that's RNG. Is Minesweeper ASMR a thing? Like, people just enjoy, like, relaxing to Minesweeper? I could see this being an ASMR thing. $36 again? I just love 36s. Slitherlink? I never heard of it. A minute 20 is still a really good score. Oh no. Gonna be here for a while. Oh, this is RNG up here. That one? Ah. I should have let you guys decide. Oh well. This is RNG. All right, top or bottom? Top or bottom? In the meantime, I'll work on the other piece here. All right, it's one of these two. It's a 50-50 shot. No one's voting? All right, I'm gonna go start it from the bottom. Oh, hey, okay. Oh, you said top? Okay, well, I'm glad I did it too soon. I misclicked. I was in a situation where I said to like do a 50-50 shot on which one was the bomb. So I was asking chat which one I should choose. All right. Oh my god, you guys keep queuing them up. Let's see. I gotta get your guys' points down. It's a valuable opportunity. Oh, okay, that was an actual mistake there. I was just going too fast. I'll cop to that one. Oh, and that one I was just being dumb. And talking while I'm playing. That's RNG on the left side there. See if we can work our way around from behind and get rid of the RNG. Hmm. 40. All right. Okay. The queue is empty. Any other challengers? Oh my god, I should have challenged you. Oh. Oh my god. I should have put a limit on that, you know? Oh my god. Alright, this is Peach Tea's Cube. Yeah, I put it on pause because it was more fun on the whiteboard. But it doesn't quite feel the same doing it in Journal Plus Plus. Oh no, oh shoot, this is my favorite firm, but I'm gonna do it wrong. Ah, I did it wrong. This is terrible. Now I have to, oh no. Okay, no. I'm restarting this from scratch. I messed that up royally. Oh my god. Wait. Oh my god, over a minute. Terrible. Okay, can I do that one? Okay, you do twice, once, twice, once, once, twice. Twice? Okay. Twice, once, twice, once, once, twice, twice, once. Okay. Do you have a cube with drawing? No, not a drawing one. I forget what it's called, but like I have one with like different size pieces for each one. But not an actual drawing. Ghost Cube? I don't think so. Got as a gift? Oh, nice. An alt algorithm? It's called the Z perm. It's twice, once, twice, once, twice, twice. When you get to this, so like That middle needs to exchange. You need the orange to go one. You need to swap like those two edges and the other pair of edges. Use a Z perm. I messed it up again because I wasn't paying enough attention. Okay, we have another. Okay, you know what? It's already partially scrambled for the next solve. Just scramble it more. Like the other day, you know, just rotating the image turns out really funny. Oh no. Yeah, I guess the is there like an orientation issue with the pictures? I guess yeah, the corners aren't interchangeable in the edges. Well, yeah. I don't think I've ever done a picture one though. Okay. I didn't inspect it for long enough. I'm getting lazy. Another Z perm. Twice, once, twice, once, twice, twice. I might be able to save it. Okay, I saved it. I messed up the same exact algorithm again though. Oh my god. Then we have the 3 Minesweepers that Anders redeemed. Thank you for the 5 bits, Phobos. No, this is RNG. It's hard to vote on this one though. I'm gonna choose that one. I don't think that one is a straight up 50-50. That one has some skewed probabilities. $36 again? How am I getting? Like, I'm a 36 machine. It's got a lot of factors. It's a good number. $32. All right, and then one more for Manders, and that's the end of the queue. A UMLS diagram for this? I've heard of like a UML diagram for a database. Is that what you mean? I had to make those for my database class. It sucked. $32 again. Okay. Based on the all-time best on 40 mines. Play this game religiously? Really? I don't know. How many mines is this? Oh, it is 40. This is the... I mean, I play Minesweeper to keep my hands occupied when I'm doing things. Or I solve Rubik's Cubes. So I do them too much. Okay, if anyone redeems anything else, I'm rejecting it. I want to go. Those of you here on YouTube, thank you for hanging out. I'll be back at some point, I'm sure. I'm sorry, Peach Tea. I don't even know what to show and tell right now anyway.